Good morning, everyone. It is my pleasure to welcome you to. Can you hear me? I hope you can hear me. Tom, you'll mention if I don't get loud and clear. Perfect. So my name is Torben Orla Nielsen. I'm science attaché here in Boston at the Danish Innovation Center and Consulate. And so for the past 6 years, my job has been to add a few more research collaborations between the US and Denmark, and today's project, CANSI, is definitely one of them. The event here marks an important moment for our project, CANSI, the Cross-Atlantic Network for System Integration. This initiative addresses some of the challenges we face when we transition to green power generation. I'm delighted to see that so many of you are here, both in person but also online, representing industry and academia, and ready, hopefully, to engage in this important conversation we'll have during the day until lunch. This seminar is, in a way, the culmination of the CANSI project, a collaborative effort that began during the pandemic, conversation between people like Almassakhi, Jacob Storstrup, Henrik Madsen, Erik Hines, about what should we do during the pandemic when we were sent home. So we decided on starting a series of webinars on system integration, and that eventually led that we built a community from the US and Denmark, and also globally, actually, that were listening into those webinars. And that was basically the foundation for CANSI. So we made it more formally, and we brought in institutions, other institutions. So we ended up with a group of institutions which from the US are Tufts University, Dartmouth College, MIT, NWell, Johns Hopkins, and University of Vermont. And from the Danish side, it's Aalborg University and the Technical University of Denmark, DTU. A special thanks to Energy Cluster Denmark, which is our project partner and project lead. You have been with us all the way. Thank you for supporting. And this project, in a way, was born out of the ambitious vision to build 30 gigawatts of offshore wind on the east coast of US. Massachusetts being the leader and pioneer in that effort, and similar ambition in Denmark and in Northern Europe. So taking that and say, what challenge does that create when we build out offshore wind with that vast amount? At its core, the project has been driven by strong research interests, both from Denmark and the US. Most importantly, it has been propelled by the dedication of the CANSI members from both countries. Most of them are present here today. Your passion and hard work have made this possible. Thank you so much for your incredible effort over the past 2 years. While today marks the formal conclusion of the CANSI project, I hope it also signals the beginning of new relationships. The connections we have built and the knowledge that we have shared lay a strong foundation for future collaboration, and I hope we will use that going forward. I would also like to extend my sincere thank you to Massachusetts Clean Energy Center for co-hosting this event, and lastly, but most importantly, also to my colleagues, Oscar, sitting in the back, and Attaché, whom you all met in the beginning, have helped tremendously to make this seminar happen today. So, before we dive into the program, a few housekeeping remarks. We have participants joining online, so please, when you are asking questions, when you are presenting, or when you are debating in the panel, please be sure to speak clearly for the virtual audience. The program, let me see if I can get this too. Maybe be a little bit difficult from you in the back, but nevertheless, the program is built up around 20 minutes time slots, so it's very easy to remember. Each presentation will be 20 minutes. So first we will have Gelen give a keynote of 20 minutes. Then we will have 2 presentations of what we call paper 1 and paper 2. And then we will have a panel discussion for 20 minutes. The first panel will be moderated by Erik Hines. Then we'll have a coffee and a bio break. And by the way, there'll be tea in the coffee break because there wasn't any tea in the morning here. So, but there will be tea in the coffee break. It doesn't make sense, but it is like that. And then we'll return, and then we'll have the two other presentations, also 20 minutes for each, and then a panel. And the second panel will be moderated by Elizabeth Wilson in the back from Dartmouth College. At the end, we will have a bit of lunch, which I'll hope you'll all be joining. So with that, let's begin. I'm sure this will be an inspiring day, and thank you all for being here and for your commitment to advancing green energy, green transition, and sustainability. Now I'm pleased to introduce our first speaker and co-host, the Chief Climate Officer of Massachusetts Clean Energy Center, Gelen Nielsen. Is yours.
Thanks, Torben, and good morning to you all of you here and all online. I think there's an emerging theme of collaboration. Eric and I were just down at the Woods Hole Oceanographic Institute yesterday, joined by colleagues, my colleagues from the Mass Clean Energy Center and I think new emerging partners at the National Renewable Energy Lab to discuss a new area of collaboration and opportunity around primarily around offshore wind, but about the energy transition more broadly. And as I think about that, and I think about some of the pressures we're facing, most notably the recent federal election here, the need for interstate and indeed new collaborative models and new approaches across the Atlantic, between federal agencies and state agencies are, I think, more critical than ever. So I just wanted to reflect on that at the outset. Thank you, Torben, for this opportunity. I'm happy to talk briefly about the role that the Mass Clean Energy Center plays in growing the climate tech industry here in Massachusetts while helping the Commonwealth meet its ambitious climate goals. And I'm going to reflect briefly on some highlights and challenges with regard to the energy transition here in Massachusetts. I think I probably will speak for less than 20 minutes because I'd love to open up an opportunity for some Q&A and dialogue, perhaps briefly at the end. So I'm really grateful for the opportunity and this dialogue on a variety of energy transition topics over the years with our colleagues at Innovation Center Denmark in Boston. A little bit about myself. I live in the city of Boston and have for about 20 years. I've been working at the Mass Clean Energy Center for, it'll be 13 years in a couple of weeks. And before that, I spent about 5 years working at Boston City Hall at the municipal level. So for those of you who don't know, the Mass Clean Energy Center is the state's clean energy economic development agency. And we are charged with accelerating the growth of clean energy and climate tech sector here in Massachusetts. You can think of us as the tip of the spear with regard to innovation on driving economic impact related to and addressing and responding to climate change. We do this to spur job creation, deliver statewide environmental benefits, and secure long-term economic growth for our residents. Our work spans 4 areas of climate impact. We help climate tech startups, so early stage companies grow and accelerate towards commercial viability across a wide variety of verticals within the industry. And we do this through competitive grant programs that are designed to meet certain funding gaps and through equity investments. We have a portfolio of over 30 companies, Massachusetts companies that we've invested in. As far as our track record there is concerned, over the last decade or so of making those investments, we've supported over 900 companies, invested about $654 million, and those companies have gone on to leverage over $2.6 billion in private and federal capital. So pretty good leverage with regard to our investment in early stage companies. So that's the first bucket. The second bucket is that we design and manage innovative market transformation programs that accelerate adoption of critical climate technologies in the building sector, the transportation sector, and on the grid. helping the state to meet its ambitious climate objectives and really push that market adoption curve to the left. And so, for example, under this suite of programs, we helped launch the state's heat pump market, the state's energy storage market, the market for multifamily affordable housing, passive house construction, and we've accelerated the electrification of commercial fleets and the construction industry's embrace of low embodied carbon building materials, including, importantly, concrete and steel. The third area is offshore wind. And of course, there's great alignment there between our interest in growing that sector as the kind of the first staging area, if you will, for offshore wind in the country, and the alignment with Denmark and our other European partners. And we do this through a range of investments in infrastructure, in our purpose-built port in New Bedford, in the Wind Technology Testing Center across the Charles River in Charlestown, the largest indoor wind blade test facility in North America, through investments in workforce and a wide range of other studies and efforts designed to de-risk and accelerate and support the offshore wind industry. And then finally, the fourth area of work is our workforce development suite of programs in which we're supporting institutions, both public and private, that provide workforce training facilities and opportunities to workers that we need to meet our interim climate objectives. So clearly, we do face some headwinds at the federal level here in the US. There's no doubt that in a matter of months, we strongly anticipate a far less supportive partner at the federal level. And this is why we could not be happier, nor could the timing be better about the passage of the Mass Leads Act. And this will kind of marks a new chapter in the development and growth and impact of the Mass Clean Energy Center. It'll be critical to our advancement of our climate objectives, as well as the growth of the climate tech sector companies here in the Commonwealth. And this was a bill that was signed just a couple weeks ago by Governor Healy. The Mass Leads Act will unlock hundreds of millions of dollars that MassCEC will administer over the next 10 years. And while details still need to be worked out, these funds will generally support climate tech testing, demonstration, pilots, and manufacturing, and while making Massachusetts more competitive with regard to attracting and retaining, particularly growing and scaling climate tech companies, and will build on our roughly 12 years of leadership in supporting predominantly early stage clean energy and climate tech startups. So I think the one key takeaway from this is that Mass Leads will really provide new resources, whereas our support for climate tech companies generally tailed off when they reached kind of technology readiness level 7, 8. This will allow us to expand our support to climate tech companies and help them grow and scale here. So specifically, there'll be $400 million in new bond funding for us, with two large buckets: $200 million to support climate tech companies as they innovate, manufacture, commercialize, and deploy their technologies, and $200 million to support offshore wind economic development specifically, and then up to $300 million for a new tax incentive program, somewhat modeled on the very successful tax incentive program that former Massachusetts Governor Deval Patrick introduced more than a decade ago, that really helped push Massachusetts into a leadership position with regard to the life sciences industry. And this will again help support scaling climate tech companies. The bill further establishes a new climate tech definition. So historically, our work has been not exclusively, but primarily limited to clean energy plays, clean energy technologies, with some exceptions. And this law expands MassCEC's scope such that we can begin to support adaptation and resilience technologies and companies. So again, this really marks the beginning of an exciting new chapter for the Mass Clean Energy Center and for the state's support of the climate tech industry. So again, thinking about our anticipated challenging environment at the federal level, this is a really important moment, as noted earlier, for states like Massachusetts to lead on climate, because I think we'll, again, unfortunately, see that leadership ebbing at the federal level. And so some examples, Massachusetts recently collaborated with Connecticut and Rhode Island on New England's first multi-state offshore wind procurement. This is very exciting. It will enable project development up to 6,000 megawatts of offshore wind. We are charging forward with clean transportation. We're launching innovative programs to support deployment, for example, of curbside EV charging infrastructure to support EV adoption among Uber and Lyft drivers, who, by the way, are some of our highest mileage drivers, to support EV charging deployment in urban areas, and to support deployment of charging infrastructure to support medium and heavy duty vehicle electrification. We're dramatically increasing our investment in workforce development training programs and infrastructure, critical to training the tens of thousands of workers, particularly electricians. We'll need about 30,000 additional electricians by 2030 to meet our economy-wide electrification objectives. Our utilities are launching, I think, very ambitious neighborhood-scale networked geothermal projects, which is, of course, an attractive option to electrify the built environment and an important step toward transitioning away from natural gas heating. We have a new state climate bank, relatively new, launched earlier this year, that's rolled out its first product, the Energy Saver Home Loan Program, to help low and moderate income homeowners decarbonize and electrify their homes. And we worked really hard to build consensus around a new path forward with regard to clean energy siting and permitting due to NIMBY concerns and a variety of other challenges. It's been very difficult for the state to meet its clean energy deployment objectives, and updating and improving our siting and permitting regulatory regime and protocols will really help, I think, accelerate the much needed deployment of these clean energy assets across the state. And I think it was also a great example of the Healey-Driscoll's administration, I think, really thoughtful engagement with a wide variety of stakeholders, and then working in very close partnership with the legislature, and finally getting to yes on that very, very important reform. But again, I want to underscore that while we're making this progress at the state level, we will face these new headwinds at the federal level. And while there are certainly more opportunities for collaboration, and there's much we can learn from our peers in other climate leading states, we are often in touch with our partners across New England, in New York, for example, and in California. I think that there's also much we can learn from dialogue and exchange, as we are here today, with our climate leading peers in the international community. And that's why dialogues like this are really more important than ever. I can point to the Mass Clean Energy Center's engagement with our counterparts in the UK, in India, in Germany, the Netherlands, Canada, Chile, Spain, and of course Denmark, and so many other nations over the last decade. In my time at the Mass Clean Energy Center, that have helped shape our understanding and approach to everything from microgrids to the emerging hydrogen market, to building decarbonization, to, of course, offshore wind, transportation electrification, grid modernization, climate finance, project development, and so much more. And are any of us surprised to learn that we face so many of the same challenges? Our economies may be different, our political frameworks may be different, but we face so many of the same fundamental energy transition questions, challenges, and opportunities. And particularly, I'll highlight a few, I think, specific to Massachusetts and Denmark, but as well as beyond. Demand flexibility is increasingly critical to meeting our clean energy integration objectives here in Massachusetts. I noted in a smaller conversation with Torben and a few colleagues yesterday that we'll need about as much demand flexibility in Massachusetts to meet our clean energy integration objectives in 2050 as we have now in all of New England, all of the ISO New England area. So a dramatic increase in demand flexibility. We face growing energy demand in the form of data centers. How can we address that? That's a challenge that is not So not yet particularly challenging for us here in Massachusetts, but we're seeing it in other states, and we anticipate that increasingly it will become a challenge here in Massachusetts as well. So I think there's much we can learn from each other. We're very interested in, we have largely legacy steam fed district energy systems. We're very, very interested in the low temp district energy systems that I know are in Copenhagen and perhaps in other parts of the country. And I think there's a lot we can learn from you in that regard, as we're just beginning to take our baby steps with regard to looking at district scale energy systems, again, as we think about moving away from natural gas heating, which is the predominant fuel source to heat the built environment. There's no doubt that we face an array of technical challenges with regard to the energy transition, but as noted briefly, we also face project finance and customer adoption challenges and the need to invest in novel finance products and business models to address those barriers. So I think there's also a rich area for exchange there. And then there are so many other questions faced by climate leading countries and subnationals. What are the most cost-effective approaches to intervene in markets critical to meeting our emissions reductions targets, where market forces alone are inadequate and climate tech adoption simply too sluggish to meet our ambitious emissions reduction objectives? How can we make necessary investments in our electric grid and begin to transition away from natural gas while protecting our most vulnerable citizens? How can we accelerate the pace of innovation, knowing that climate solutions still in the lab or not yet even identified are critical to meeting our emissions reduction objectives in the long term, and they may take a decade or more to achieve commercial traction and impact? How can we finance climate adaptation, decarbonize heavy industry, and electrify our ports, and on and on and on? There are so many shared challenges, so many opportunities to learn from each other. What role will advanced nuclear and SMRs play in our future energy mix? And what projects, what must we support now or in the near future to ensure those clean resources are online when we need them in the out years? So on these and so many more shared challenges, we can learn so much from each other, particularly as we are beginning to explore many of these emerging markets and technologies. So as some doors are inevitably closing at the federal level, we must work to open others and build new bridges of collaboration and shared learning. Our shared climate challenge is unaltered, regardless of the recent election results here, and our resolve and focus on accelerating the energy transition must continue apace. So I look forward to more cross-Atlantic collaboration and to learning from each of you today and beyond. And thank you for your time, and I'm happy to take a couple questions if we have a minute or two.
Any questions? Thoughts or remarks?
Get it. Kevin Almassakhi, thank you so much for that. The leadership of Massachusetts is tremendous. And so my question is, this kind of ties into you stopped into both of you. That's note that so it's key for individual, local, state, federal entities to work led together, which sweet out to kind of scale and all of that. And then can you talk a little bit about the offshore wind collaboration with the company where I ended it? We need to talk more about that in light of the change with the federal leadership. What are the conversations happening at the leadership level here in Massachusetts about linking together all of the states that are leading or wanting to lead?
I'm glad you asked that question. We have in fact begun some dialogues, and I have to give credit to my wonderful colleagues at NYSERDA who reached out to me, the New York State Energy Research Development Authority, right? I so often use the acronym, I forget the translation. And believe it or not, the last time we had this type of I'll call it climate leading state dialogue was 2016, not surprisingly. you can connect the dots. And I was very happy that they reached out, and I reached out to colleagues at the California Energy Commission. So we've begun this dialogue. We're beginning to think precisely about your question, which is, what is the nature of this collaboration? What are the very specific ways in which we can begin to collaborate more closely with other climate leading states, and in a way that both kind of can be kind of a support network, but such that we can also move forward more efficiently. What can we learn from each other so we're not duplicating efforts, particularly with regard to energy innovation and emerging markets. So we've just begun the conversation. I'm glad you asked. We're still shaping it. And I think based on my conversations with Torben, I think, again, our ongoing, although very episodic, dialogue with the international community, both here in Boston and of course around the world, it would be wonderful if we could figure out a way to kind of integrate where relevant parties, institutions, governments, NGOs that are doing this work globally and bring them into that dialogue, because clearly we need as many voices at the table as possible.
Thank you. Yeah, I'm sure it's an international context that you
I'd just like to, I'm from over in West Denmark, I'd just like to really appreciate your efforts here. The overview you provided is really impressive. And I think you really, to my knowledge, tick all the boxes that we need to address in this transition that we're in. And I'm certainly happy that we can take that knowledge back, that you're also working on it. I get slightly worried about the innovation ability in Europe when you're so advanced here. So that will be a challenge for us, I think, in Europe also with the IRA, that is really pushing together with your state funding.
Well, I'd be happy to talk more about that. And I think that, candidly, I think many of us in, smaller groups will often acknowledge that particularly Europe is substantially ahead of the US with regard to kind of energy transition policy frameworks generally across all sectors. But particularly I think I shared this with you, Torben, but in dialogue with our German counterparts years ago, they kind of acknowledged the same, but they said at the same time, we're very envious of the innovation ecosystem in the US generally, and particularly in the handful of areas, Silicon Valley, the greater Boston area, Texas, on, the Austin area in Texas, where we have these clusters. And they attributed that to the American tolerance for entrepreneurial failure, which allows entrepreneurs to there's an incentive to experiment over and over and over again. And I thought that was a very interesting kind of cultural observation. But we'd be happy to talk about the kind of very concrete programs that we have to support early stage companies, and how we balance risk and investment.
Yeah, I have Madsen technical development. I don't need to my question then would be, I think we can learn from what you're doing with the executive program with the financial sector. So I would like to maybe look at time now, but I would like to learn a little bit more about how you succeed with that, how you did it. I don't know if you can briefly elaborate. Is it up and running? Does it work? And do you collaborate on a daily basis with the financial sector?
Yeah, I would say briefly that there is this funding, which it may be threatened again in the new administration, but greenhouse gas reduction funding out of the EPA, Environmental Protection Agency, that is kind of designed to support state level climate banks or green banks. But states are also have skin in the game and are also investing in those. The state of Massachusetts has done that, invested, I believe, 20 or 30 million in the development of, so an initial down payment, if you will, on the state's climate bank. And the concept there is fairly straightforward, which is to offer concessionary capital, patient capital, lower interest capital to support specific projects, in this case, decarbonization and electrification of low to moderate income households. But that's just the first product. And I think there are many, many more opportunities for climate finance supported perhaps with novel insurance products to deal with some of the risk to support a wider variety of climate projects, including, for example, solar deployment in for unrated businesses that might have a 100-year track record, but are nonetheless unrated and can't get the financing for a 1 to 200 kilowatt solar system. But a novel finance and insurance product can help unlock that private investment.
Jacob, you have the last question. After today's event, we'll meet in the cancer group and discuss things going forward. I think that we agree that, as you also kind of been alluding to, it's a very important conversation, so we'd definitely like to keep that going. Maybe we should consider to extend the partnerships on either side. So far, it's been mainly academic, but I think it's important to include also other agents, maybe the policy level, maybe industry. So for our discussion this afternoon, would you provide your perspective on how would you like the conversation to proceed after this?
Yeah, happy to. And I suspect, I don't know, Eric, you've probably thought about this too, but I think in my mind, the most powerful and impactful delegation compositions include academia, private sector, and policymakers of public sector, and to be clear, from both the state and municipal or local level. And those kind of exchanges, I think, are very, very valuable. Not just because those particular market actors and decision makers are critical to working together to move the energy transition forward, but they learn from each other on the trip when you have those exchanges. Yes?
Matsen, also from the Technical University of Denmark. Really nice to hear all that you do. And very interesting about this cooperation between China and advanced states. I was just thinking, coming from the MIT workshop in DC at the beginning of the week, there was some talk about, how researchers like to go to the focal point, and maybe that has been at federal level, but that focal point for climate research or bringing forward results within research could be such a cooperation between the climate advanced states in the US, and whether you think that you can kind of attract researchers and their, because we can't go everywhere, right? We kind of need to have as high as possible impact with our research. But maybe that could be kind of a way to leverage more of the research also through this concept. I mean, together.
Agreed. Yeah, I think that will be an important component of it. We do support research here, but it's usually applied, not basic. And much of that support has come from the federal level, but I think there's certainly an opportunity for that to be part of the exchange.
Thank you, Gelen.
Yeah, wonderful.
And now I've been told to stall a little bit while we are downloading the next presentation. First of all, I'll apologize to Gelen that all through your presentation your name was even though we share almost the last name, not the first one. So. But I'll put the next speaker on, because now we will dig into the presentation of the 4 papers, and as mentioned in the beginning, we will do it in 2 sections: a presentation of paper 1 and paper 2, and then a panel discussion. And the first paper is going to be introduced by Professor Eric Hines, whom many of you know from Tufts University. He was actually one of the first people I met when I came to Boston. You invited me for coffee at Tufts University. So as the lead for Tufts offshore wind energy program, Eric has really been instrumental in advancing innovative solutions for renewable energy infrastructure, particularly in offshore wind. With extensive experience in structural engineering and a passion for sustainability, your work has bridged the gap between academia and industry and public policy to address critical challenges of the green transition. Henrik has been one of the main authors of paper 1, together with Brian Mathiesen, sitting here, who is a leading figure in the field of renewable energy systems and sustainability transition in Denmark, and also a TV celebrity. We learned that yesterday when the Canty Group was visiting Vineyard Wind, and on the bus back from Vineyard Wind up to Boston, Brian was called up by one of the major broadcasting from Denmark for an online interview. So not while driving, but in the bus, he made a comment on the recent development in solicitation in Denmark, which actually it's fair to say that was a bump on the road in the Danish green transition. But I think that's also what the green transition is about, that we will face a number of challenges and we need to overcome them. So we don't need to be very, very sad about that. Brian is internationally recognized for his work on smart energy systems and energy planning and a lot more, but with a strong focus on integration of electricity, heating, transport, sector coupling. His research provides practical pathways to achieving sustainability and climate neutral energy systems. His expertise has shaped not only academic discussions, but also informed politics, both on a national and international level. So please join me in welcoming Henrik and Brian. I don't know how you are going to split it, but that's up to you.
Good morning, everyone. Torben, thanks for having us here. Brian's given me permission to just move through this presentation quickly. So before we get into this, though, Torben, I met you when you first came. That was before the pandemic. I really think the energy transition is about building things, and I see you as a builder, someone who has patience and perseverance and who really understands people and who understands what it takes to bring people together. So I just want to thank you for all the work that you've done while you've been here in Boston. It's really been a significant contribution, and we're all very appreciative. So thank you very much. So we have this energy transition, and as we get further into it, we understand more and more that it's about language, and it's about, can we speak the same language, and how do we communicate? Because we can't make anything happen if we can't communicate and understand each other. And so this particular paper is a practical framework for understanding the basics of an energy transition, which boils down to basically how many wind turbines and how many solar cells do you have to build, and when do you have to build them by, and then how do you manage the grid to do that, and then how do you cut down the demands on the grid. And so first of all, how many gigawatts do we need? Well, this is a framework I've been using because I can remember it. So we had a goal for 30 gigawatts of offshore wind by 2030. New England has about 30 gigawatts of electricity capacity. I think we need at least 300 gigawatts of offshore wind by 2050, and 3,000 gigawatts of wind and solar is not a bad number for the United States by 2050. So these are the numbers that I keep in my head. I can't forget them because they're too easy to remember. And then what has gotten in the way? It wasn't that long ago, less than 10 years ago, when you started to read about the energy transition, you weren't reading in terawatt hours. You were reading in quadrillions of BTUs. That's still how we talk a lot of times in terms of heat. Millions of tons of oil equivalent, exajoules. It's just, you have to sit down and actually do all of your 11th grade chemistry to figure out how to convert these units from one to the other. And then once you get the conversion factors down, you realize that there are different conversion factors going from BTUs to terawatt hours depending on which energy source you use. And that's in some appendix F somewhere down in a document that no one reads from the Energy Information Agency. So it is a very difficult task to do some very simple algebra, and it's confusing and it messes up the language. And then if you think about Europe and you think about the United States, Europe has a set of different countries that all have different targets. The United States has a lot of states that also all have different targets for the energy transition, and energy is a state level policy in the United States. So it's really important when working with the United States to understand that states are what set energy policy in the United States. And so we got together and we said, well, let's just take a survey of the latest best reports that we can find that our group has knowledge of. Let's put them together let's put the renewables up top. Let's just order the tables so that they're all ordered in the same way so that we can compare apples to apples. Very simple moves. And then let's talk about them and let's average them and let's think about, well, what are we talking about? And so this is just a smattering of some of the particular studies that we looked at and that we talked about. And our object was to make everything as simple as possible and to really boil it down to the most important issues. So as long as we're within 10%, 20%, even 30% of a reasonable answer, we're good. And we're not worried about the 2 or 3% on the margins. This is a study that Brian and I have added recently in response to our conversations with Energinet, which is the Danish TSO, about the 10-year development plan. And we'll notice in a minute that this 10-year development plan shows numbers that are actually quite consistent with the numbers that Kanzi came up with. And so it's we're at this point now where at a macro level, there's a reasonable amount of convergence between the studies. To get to that point, of course, this is what it means to dig into this. And who has time to do any of this? No one has time to do any of this, and no one has time to read the reports either. So we need a very different way of understanding the energy transition, of understanding basically gigawatts and terawatt hours is what it comes down to. And again, the number of wind turbines and solar cells that we need to build, and then the other stuff that needs to happen in the meantime. And so one thing is there's some rather simple algebra but you have to do the algebra in order to figure out how to go from electricity production and power capacity. And in between that is something, an average annual capacity factor. And people seem to really get stuck on, but that capacity factor for this region and this municipality and this area. And then people sort of get confused. And I've noticed over the years that the conversation just stops. And our goal is to keep the conversation moving and to keep as much of the conversation intact. But the pieces that want to slow the conversation down, we're trying to shed them right now because hundreds of millions of people have to understand this in order for us to be able to accomplish the energy transition. And so we developed a synthesis. The synthesis is everything here is written in terawatt hours in terms of primary energy supply because there are retail sales. There's capacity. There are a lot of ways of talking about this. Again, it's a question of language. So I assume that folks have the paper. But if you look down at this, total primary energy supply in Europe in 2022 is around 16,000 terawatt hours going to 10,000. United States are around 11,000 terawatt hours going to 15,000. That 15,000 can be, in my experience, anywhere from 10,000 to 20,000, depending on which report one reads, how one thinks about it. And how one processes the data. And then we just recently, before we finalize the paper, want to connect this to the 10-year development plan from 2024 for Europe. And you'll notice here that the 16 and the 10, and the 16 and the 10 are the same. So that's the headline, is that we have some numbers that all of us can remember, and those are the ones that we ought to be focusing on until they change a substantial amount. We also looked into this question about area and per capita. And so these are interesting questions, and there are some high-level observations that can be taken from these numbers. And I think these are observations that are going to be clear to people. They make sense when you read the paper. We can also see that ideally, we in the United States, we have the most wind here, here, and here. And so you have to get it to the other places. We have the most solar here. And how do you get it everywhere else? Well, we need a grid. And so this grid then starts to happen. And we're developing this grid and figuring out how to manage it. And so what are our conclusions? That US PES values are approximately 50% higher in Europe in 2050, based on the studies we looked at. Europe is working toward efficiency via demand response and sector coupling. This is what paper 2 is about. And this is something the United States is also very interested in. Massachusetts is interested in. Gelen, from the point of view of Massachusetts, I really think one of our key connections to Denmark is in learning more about this and the sector coupling. And this is something we'd like to see, that we'd like to leverage both in the relationship with Denmark and in the relationship with the National Renewable Energy Lab. So, and then also working towards synthetic zero carbon fuels. And this is paper 3, Power to X. And so I'm just going to take another minute or two to run through a couple of different slides. That this is a slide that's credited to Princeton University and the Net Zero America. They have all these different scenarios. And the questions is how are people dealing with storage? How are people dealing with the grid? And how are people dealing with hydrogen? These are kind of the high level issues. And so we just sort of include, you can bury yourself in Sankey diagrams, but it's reasonable to sort of keep track of the high level issues, the grid and the storage. and how does hydrogen factor into the storage? And again, paper 3 talks about that. The question between terawatt hours and gigawatts and capacity factor is, if you keep 2 of them at 2 significant figures, you're going to get another one that you have to calculate, and it's going to be a weird number. And so what I've triangulated on is I just let the capacity factor be a weird number, because it actually varies by several percentage points anyway, depending on where you are and how you assess this and what study you're working on. And so whether a capacity factor is 0.45 or 0.46 really doesn't matter. What matters is, can people remember, again, the terawatt hours and the gigawatts and hold on to the numbers as opposed to tacitly ignoring them. There's also a possibility to really boil this down into gigawatts, and thinking about Europe looking at 800 gigawatts of onshore wind, the US looking at 1,500 gigawatts of onshore wind. Offshore wind, the European numbers are about 250. The US average numbers are about 150. I think those are low, you'll see in a second. And then solar PV being 1,200 gigawatts and 1,700 gigawatts respectively. These are some numbers that I created really without the permission of my colleagues who are co-authors of the paper. It's in the appendix buried somewhere, and it will stay there until someone tells me I have to rip it out. But I took the numbers and I just turned them into numbers that I could understand and remember again. And I bumped up the offshore wind number to 450 gigawatts. And so you see the terawatt hours, the capacity factor, and the gigawatts. And I think that we're in a place where we can start to talk about, it's not about is nuclear in or out. Both cases have 1,000 terawatt hours of nuclear. It's not a case of whether biomass is in or out. You can see the carbon-based fuels are out, okay? And then how do you add these up, and where are the big numbers? And then finally, the thing I want to end on, and I want to acknowledge one of our panelists, Kevin Knobloch, has joined us today. This is something that we got into, again, as you said, Torben, in 2020. We were all sent home. We didn't know what we were going to do. And so we started hatching plans for the future and thinking about this. And we started wondering, actually, about, well, how many gigawatts were we going to need to build of this or that? And we just started with a map of the country and what were the demands in 2019. We're about 4,000 terawatt hours. And we decided just to double it and see what happens. And then ultimately created this with a pencil. And the reason we did this with a pencil was to demonstrate the level of technology that was involved in thinking through this. But this is actually where things are at, because if you use a very fancy computer, you're not going to get results that are that much better than what you get with a pencil right now with all of these issues. And this is something culturally that's very important for us to understand, so that we maintain a sense of agency as we move through this. And because you can do this with a pencil, you can turn it into a homework assignment. You can take something that took a whole bunch of professionals several years, and you can give graduate students and upper class undergrads 2 weeks to think about this. You give them a map of the country and you say, okay, give us an energy transition. Here's your blank map, color it in with a pencil. Here's where the wind is. Here's where the solar is. This is what the grids look like. In case it wasn't complicated enough, we just decided to give you some grids that are complicated. And then here's what the regional transmission operators look like. And this is what the ISOs and the markets look like. And now come up with some regions of the country and put gigawatts and terawatt hours in there and work on these. And so these are different. This is the results of different student work on this. And you give this map to different people and you'll get different answers, which makes a lot of sense because we have different regions, we have different points of view. And this is what's already happening in reality. So this is about as real as it gets. When the students sit down and start to think about this, they all do their own assignment, then they do it again in groups of 5 where they have to come together and compromise. And they think about other things. They come up with ideas about the macro grid. They come up with ideas about the gas and the oil distribution throughout the country. They think about comparing different regions and understanding this, and they start to read the reports that are being written, and they're in a place to critically evaluate all of these reports. And so I think with that said, the question is what does someone need to know about the energy transition to be able to read these reports critically, to engage them, and then to understand for themselves what needs to happen next? And this is the object of paper 1. So thank you for your attention.
We will quickly move on to the next paper. Unless there's any comments. And the 2 next speakers will be Professor Henrik Madsen, a distinguished academic from the Technical University of Denmark, DTU, He is renowned worldwide for his groundbreaking contribution to mathematical modeling, data science, and energy systems, and one of the most cited researchers globally, I believe, maybe the most cited in his field. With over 3 decades of research experience, Henrik Madsen has authored numerous of influential publications and collaborated extensively with industry leaders, making his work both academically significant and practically impactful. Together with Henrik, I don't know how Henrik and there you are, Mads. 50-50. Okay, but it seems to you may be starting. So we have Henrik, sorry, Mads Almassakhi just next to me here. Yeah, a Danish-American researcher. And thereby a true bridge builder between the US and Denmark. The spirit of cancer, you could also say. Mads from University of Vermont is a leading expert in power systems and energy optimization. As a faculty member of electrical engineering, Mads research focusing on designing innovative control strategies and optimizing tools that enables the integration of renewable energy into the power grid. Mads is also an entrepreneur. He is a co-founder of Packetized Energy, a company that develops smart energy solutions to support more flexible and sustainable grid. So please join me in welcoming both Mads and Henrik. And
it's very nice to be in the Danish audience because I didn't know how to say my name right. People always ask me, how do you say your name? And I say, just like that. And so it makes a lot of sense. And so I am from the other side of New England, also known as Burlington. And what's exciting in Burlington is that we're on the horizon. We're looking at a new center. So we've just started a new center called CREATE, Resilient Energy and Autonomous Technologies. We have about 40 researchers working in this area, most of whom are PhDs or PhD students. And so it's a really exciting time in Vermont. We have a lot of interesting partners, most of whom are in the energy space. Some at the intersection of autonomy, control. And so we're starting to build some demonstration facilities, both on the campus and off campus. And so we have electrolyzers, PV, batteries, power electronics, kind of coming together with real grid models, distribution feeders, transmission systems as well. And so we're trying to build effectively a digital copy of Vermont's electric infrastructure to understand and validate and quantify the value of different technologies, whether they are controls, autonomy, or energy systems. And so, unfortunately, it didn't quite translate. But some of the, jumping straight to paper 2, I think just want to summarize very briefly at the highest level, what we're thinking about is the fact that transmission, nuclear power, and offshore wind takes a lot of time and a lot of billions. If you look at PV, batteries, other distributed solutions, they can be deployed really fast. And so if our goal is to reach the mountain of decarbonization and electrification, what we need to do today is sprint. The easiest way to sprint is, on paper, PV, batteries, and distributed solutions. And that's what we're seeing today, right? Transmission projects canned basically month by month. It's super hard to move forward on very large scale transmission, nuclear, and any of these billion-dollar projects. They require patience, and today I don't think we have the patience that we need to. Anyways, and so the goal really is, I think we're down here. What we believe in paper 2 and what we argue for is that there is significant value today to really think about full-scale demonstration projects that evaluate an advanced state-of-the-art, state-of-the-science, state-of-the-practice for coordination architecture. So architectures, control architectures that coordinate these resources that are popping up everywhere, whether we like it or not. And so speaking of trends, things we don't like, things happen over time. And so if you look at computing, this is recently from a cleaning up podcast episode that talked about exponentials, the role of what's it called? Exponentiality. It's talking about exponentiality. And so if you look at Moore's law, right? We know Moore's law and ignore that infinity should be here. So Moore's law says in 1961, a gigaflop of computing was very expensive. Today, it's basically free. Infinite time improvements. Solar PV has gone through a 400-time improvement, right? Sensors have gone through 1,000 times improvement in costs, right? What we can do and measure today is effectively Amazon material, right? You can book it, order on Amazon. We did this with packetized energy. Basically leverage the very cheap sensors to do really neat stuff for the grid. And I guess it didn't really transfer, but it doesn't matter. The last one here is batteries, right? Has gone through 150x reduction in costs. And so these trends are happening. I'm a big fan of them. People who know me call me a friend. And so the question then is, what does the future hold? Right? The future is really exciting in this space because we see that utilities and companies today are competing over their virtual power plant roles, right? And importantly, the technology behind these virtual power plants is not really understood, in some cases by either party. When you talk to Sunrun, Sunrun says utilities are a culture of no, 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 and I can scale fast. This is not a complementary relationship, but really a competing one. And should utilities compete with companies to design that future grid? And if you ask Google, which laid out the architecture, this is Google X, laid out the architecture recently for the digital grid of the future. One of their key recommendations is that flexibility becomes the defining characteristic of the grid. Right? How much can the grid respond to changes, both at the distribution level and at transmission? And then you at the same time have social communities that are embedded with this grid. Right? We are people that use devices and not the other way around. And so we have to think about energy burdens and the trade-off between energy burdens and energy limiting behaviors. Energy has costs, real costs, and reliability too. And so what does the grid of the future look like? If you ask New York, they have very promising grid of the future studies. Their vision laid out in recent policy documents lay out virtual power plant and distributed energy resources as the backbone of that grid of the future. Talk about Department of Energy has invested $144 million in a New York utility project called Future Grid Project. And if you ask Seagray last month, they trademarked Grid of the Future. And so I missed this conference. I was not there, but maybe somebody was. And then we know what the Grid of the Future looked like. And so our view in paper 2 is really that the system that we're looking at, the distribution system in particular, the power system, right? This is a textbook from the 80s, the 90s, 2000s, 2010s. This is what the power system used to look like, right? Cheap solar, cheap wind, carbon policies, electric vehicles, smart thermostats, batteries, cool new induction stoves with batteries installed, that data centers, right? System is really complex today. Where is the grid? Every one of these devices have a power electronic interface. They're basically circuits doing all the control, all the sensing, all the data being collected at each of these nodes. What is the grid? Is the grid just the wires connecting different components, or is the grid the whole thing? And so I think as we move towards this distributed energy future, the question becomes, what is the grid? Is the grid changing as we add billions of devices, right? What does this interdependent system look like? Is it a system or is it a chaos? And so, we're talking about billions and millions of distributed energy resources. The flexibility that we have today that makes the grid work, makes it reliable, that flexibility comes today mostly from power plants. Thermal generation is providing inertia. Thermal generation is providing reactive capacity. The grid is stable because we have power plants. In 2050, estimates are that 50% of flexibility will be provided by distributed energy resources from the demand side and batteries. That's a different view of what the world looks like. Right? Today, we have DER operators and electric utilities being oil and vinegar. They don't mix. No emulsifying agent. We have Jiggershaw at DOE selling virtual power plants as the solution to this problem. This is a really neat chart. I love the idea, but there are so many open questions. How do you architect it? How do you orchestrate the ERs? How do you design the power electronic interface? What are standards? There are no standards today. You go to Energy Hub, you go to Virtual Peaker, you go to any of these aggregators, they have different approaches to solve the problem, different assumptions. What role does the grid data play in this? Are devices aware of the grid? Are the grid aware of devices? Are they one system or two different systems? Oil and vinegar. Markets and regulation are catching up. Policymakers lack software tools to understand impacts of technologies, of decisions. Human factors, ensuring an equitable grid access, are all missing. Communications, I love this idea. That chart on the right shows communications, and that's just how it's going to be, but there are no standards, right? Every device manufacturer have their own APIs. There's no commonality, no common language. And so our argument, even with broken PowerPoint slides, is that we need grid architectures that are adaptable, that are scalable, that are solving these very big challenges. Interdependencies between infrastructures. Market structures are heterogeneous between Europe and the US. And what I think I'm pushing pretty heavily is we have intelligent networks, we have intelligent nodes, and we need some kind of control co-design problem that needs to be solved. This is not a one-year problem. We can't solve this tomorrow. We need to think about this over the next 10 and 20 years. And so there is really hard problems to solve. There are really big challenges. And we can't solve this piecemeal approach. Right? Massachusetts CEC is great. NYSERDA is great. California has their own CEC. Great. Everyone else does not. And we need common frameworks, common solutions, and common architectures. We were able to do this for the internet. The internet has really good ideas. Internet is scalable and adaptable. Internet solved a lot of challenges. And so one of the examples of paper 2 is the fact that we can think about internet approach to data packets as a mean to manage energy packets. And so we developed technology, and sorry for the miss. We developed technologies centered around internet to packetize energy across coordinating DERs. And so we built software platforms to manage and coordinate resources using similar concepts like random access protocols that makes the internet work. And so we had an ARPA-E project for 7 years, funded multiple times. We deployed it in the field. We had offices in Massachusetts. We had offices in Vermont. We built out a company called Packetized Energy, upper right corner. We demonstrated the technology in the field with over 200 devices in people's homes. We showed that it could perform, these 200 distributed energy resources could perform frequency regulation, which is a form of flexibility, at the same capacity or better than almost any thermal generation plant. Right? The only ones that really beat us was a single stationary battery. And so we showed through distributed energy resources that we could coordinate and deliver flexibility as well as any other resource. This company was acquired 2 years ago by Energy Hub, which is sitting in New York and Vermont now. And so I appreciate your time. I'm looking forward to talk and learn more about your thoughts about the grid. Hopefully we all agree on a grid that makes us all happy. So thank you.
Full screen. Yes, 1 second. Yes, just to warm up while we're getting the screen, the slides. Thanks. So Mads outlined a lot of problems, a lot of challenges. I will try to point at some recent trends which we see in demand-side flexibility and maybe provide some hope, because I think it is complicated, as Mads indicated. And this is something we published in a paper called Some Recent Trends in Demand-Side Flexibility. So just to outline what are the benefits of demand-side flexibility, and these numbers are from Europe. It's from some European reports and projects. I was leading 2 of them actually. But there is a DNV report which actually summarizes that the consumer benefits from lower wholesale market prices and lower cost for reinforcing the grid and so on corresponds to more than 300 billion euro savings per year. And in Denmark, in particular in the northern part of Europe, we are talking a lot about energy islands. And one of the bump of the roads mentioned by, I think, you, Torben, yesterday in your introduction, which we had yesterday on offshore wind, we are looking into energy islands, and the total cost of the energy islands is around 300 to 400 billion Danish kroner. So taking the rates into account, this corresponds to the fact that we can actually save 4 times the total cost of the energy island each year. with this demand-side flexibility. But this calls, in order to succeed with that, we need edge-based computing. We need some of to solve some of the challenges Madsen pointed out. And where are we? We are in a situation where we come from large central power plants and actually we are stopping almost all the central power plants. So the intelligence now should be moved from the left hand. Historically, the intelligence was on the left hand side, but now in the future, the intelligence should be on the right hand side. And here we have big data. We have users. It's close to the users, so we have all these complexities which Mads pointed at. And just to fast forward things, in our view, in our conclusion is that we believe that when we look at things closer to the consumer on the low voltage level and so on, I don't think we will be able to set up a market for flexibility on controlling the voltage and problems with a transformer on this district. So we need to go away from this conventional market thinking and introduce control-based approaches when we get lower into the grids, in the grids, and also when we do sector coupling, also when we need to act fast. So when we need to act fast or at high resolution in space and time, we need control theory. And that's basically one of the takeaway messages from this paper, that we need to move more on this control theory. Because using control theory, we will be able to go away from this static, deterministic, and linear thinking we have in the current market, where you have the merit order bidding and so on, and you get the price. You solve this optimization problem, then you get the volume and the price this hour, and solve it again next hour, and then you get a sequence of prices. But this does not take into account the dynamics, stochasticity, and the non-inertias we have in the system. But this is something we can do by control theory and stochastic control theory, and using what we call flexibility functions, which is a key element of that. Another takeaway message from my presentation, apart from the focus on edge computing and data everywhere, is that when we get lower into the system, we only need one-way communication. So we just need to broadcast the price, and then the different devices need to react on that. We don't need to know all the elements of a heat pump and so on. That would be too complicated. We simply just need to broadcast the price. So I'm actually, as a researcher, zooming into how to build what we call the smart energy operating system, and it's just a name for a framework of models which are used for control, forecasting, and coupling things together on hierarchies. So it's models where we can zoom in and out in space and time in a way so that the forecasts are coherent in space and time. So that's a key element, and we're doing a lot of research on that today. The flexibility function is something which describes how a flexible asset, maybe a supermarket, if a supermarket has been flexible for this hour, what happens then? What is then the flexibility dynamics? Then if it has been flexible this hour, it can probably not be flexible next hour, and this has to be taken into account. And that can be done with the flexibility function. With the flexibility function, we have basically a relationship between the penalty or a price and the response, which can be the load. And if you have this relationship, then we are also able to develop a controller which gives the price, so we get the load or the voltage we want to have. So with this setup, we are able to control voltage, frequency, congestions in all levels of the grid, and so on. And this is embedded in this smart energy operating system, where we have, if we zoom out, we have conventional markets. So if we zoom out and spend time, we have conventional market. But if we zoom in on a supermarket wastewater treatment plant, then we need to take dynamics, stochasticity, and this into account. And this is done by the flexibility function, and which actually maps the static markets to the dynamics and stochasticity we have on the edge. So in a simple way of depicting it, what we have today is basically market on a TSO level and on the upper level, but basically when we get lower, we don't really have anything today. It's my view, of course, we can discuss later on. But with this hierarchy of controllers, hierarchy of modes, we are able to control things at all levels of the grid, and we are actually also able to even to consider energy communities and control things inside the energy community. So again, zooming up, if you zoom out, consider a very large scale, day ahead, we need conventional markets, we need a level. But if we zoom out either in space and time, then we need a control theory. And the controllers need to talk together, so the different type of controllers are linked. I'll be happy to talk more about that, but I don't think I have time for that. So just one simple example, which will be in our paper, is an example from summer houses in 2 areas in Denmark, 2 low voltage areas where we have summer houses. And these are 2 areas where there were a lot of problems with the quality of the grid. So we are at the same time, we have a lot of wind power in these areas. And actually they curtail the wind power very often. They curtail a lot of wind power. But what we are doing here is by using the swimming pools in the summer houses, we could actually use this swimming pool as a battery, so to help the grid, to help with grid challenges, and at the same time we could store the energy, excess energy. So instead of curtailing the wind, we can store a lot of energy in the water, and the kids really nice the very hot or nice warm water. We don't boil the kids, but we get a. So again, I don't have time to go into the details, but this is up and running, and we saved around, depending on the summer house, we saved between 20 and 40%, both in cost and CO2 emission. So thanks a lot for your attention.
Thank you, Henrik. And then it's time for a discussion and a panel. So please invite Henrik, Matt, Brian, Professor Coskun, Kevin, have a seat. And Eric, you will take it from here. And
We're going to share these 2 mics, right?
yes, exactly. Yeah. So, and we will take questions from the audience and from our online audience. They can in the chat, and Oscar will provide those.
Sounds good. Yes, can everyone hear me? We have a lot to pack in 20 minutes. Panel, I'd like to start actually by asking, I think I have a mic if this is shared with folks. Yep. So Kevin, Ayse, thank you for joining us on this panel. Thank you for your courage to just jump into this and to be in the middle of this, and we really appreciate your perspectives coming into what ultimately I think we're presented as 2 very different perspectives on the same thing. And I'd love to open the panel with your comments, Kevin, if you wouldn't mind going first, and then Ayse, general comments on the papers.
Thank you, Eric. Is on? Delighted to be here, and really especially delighted that we're having this level conversation at this point in time. We're 30 years into this grand decarbonization project globally and in each of our countries, and to be able to drill down, as these 2 papers have, and understand where we're at and where we need to go really reflects how much progress we've made. Deployment of renewable energy, energy efficiency, prices have come down. Innovation is heightening in purpose and focus and drawing investment. And what's happening is because we're at this point in time, the problems we're facing are more complex and more stubborn and more sophisticated, and will be for the whole second half or the next 3 quarters of decarbonization. So I really love the papers, in that respect. And I also love the drawing out of the distinctions between what's happening in the EU and what's happening in the US. And if you look at the at the chart, you see that we're kind of diametrically opposed in some areas, in nuclear and offshore wind. And, you know, where the EU is taking the lead in what's projected performance going forward. And some of these technologies and the US and others, we have a lot to learn from each other. And I think that the last thing I'll say by way of opening is what I really appreciate about both papers, especially the second one, is the focus on systems engineering and systems management. That you know, to note that there's significant curtailment of wind in Europe is the original sin of renewable energy, right? Those investments are precious. We need to put every clean electron to work. And so when we're talking about connecting, you know, the physical plants of homes and businesses and factories in a much more sophisticated way, we're talking about putting more electrons over the same transmission infrastructure. We're talking about highly sophisticated and complex demand side management. That's all about getting us to where we need to go to a zero carbon future with much more efficient investment. We can't build our way out of it. And the great example of that are data centers and what's happening here. The whole discussion is about how that's flipping the demand for our utilities, the demand equation, and we need more and more generation. And by the way, we can't retire those coal plants because we need to feed these voracious data centers. Where's the conversation on efficiency? How are we going to make these far more efficient? And so that we don't have to keep laying in more and more and more clean energy power. So that's what I'd say by way of opening.
Thank you. Actually, thanks for talking about data centers, because that's what brings me here. I work on data center energy and sustainability, and particularly integrating data centers into grid programs, doing data center demand response, providing data center flexibility. And great work, really interesting. I made a lot of notes throughout the paper presentations. I'd like to offer a few thoughts and maybe a few questions. So data centers are a big deal because they bring a lot of demand. And even with projected efficiency gains, we expect a lot of AI penetration in lots of sectors. So the demand is not really going to be resolved by more efficiency, in my opinion. So there's anywhere between 10 to like 40, 50 gigawatts expectation of demand in the next 5 to 10 years. So this is huge, even though I saw the 3,000 gigawatt number in the first presentation, which is, wow, you know. Anyway, so I really believe in the need to do demand side flexibility and a more controllable, more optimized grid. And this is the key to both electrical vehicle growth and also data center growth, essentially. Right now, how it's working is that data center comes in and asks for power. Like, I need 200 megawatts. And the utilities are having immense trouble meeting these demands because not only it's like this gigantic number that they suddenly have to produce, there's issues with transmission. Even if you find the energy, there's clean energy waiting to be connected in various states right now because of challenges in building the transmission. And there's challenges with volatility. So there's volatility. I was in Iowa recently, for instance, which has a lot of wind energy. The difference between the windy season and non-windy season is like they have 30 plus gigawatts of wind energy, for instance, in windy season. And then when there's no wind, it's like drops to 200 megawatts. So then how can we ask the utility to turn off the coal plant or the gas plant, right? So what's going to happen with this gap? And there's no grid scale, cheap, scalable battery technology that you can just store in summer all your solar power to use in winter. Like, that doesn't quite exist yet, right? So volatility is a big deal. And I think really looking into demand flexibility is really, really important. And I think Denmark, with its more data collection, more ambitious programs in this side, could be an example for a lot of countries. So that's one thought. Another thought is the how to make this attractive. In the US, a lot of regions have demand response programs. They are immensely underutilized in general. California retired one of the demand response programs this year because of under participation. So some thought is that, if you price it right, people will respond to it. But then, for instance, cryptocurrency data centers in Texas were doing demand response on their own, kind of like just following pricing incentives. But sometimes the utility increases the price and the usage increases. So there's a lot of counterintuitive things happening with pricing. So how do we make this attractive, going beyond pricing? One idea is regulation, but then, that's generally not a popular thing in the US to do more regulation, as you know. So how do we make this happen? So there's the optimization framework, volatility, and the right incentives to make this attractive for electrical vehicles, data centers, and all kinds of consumers. So those are some initial thoughts. Great work. Thank you for inviting me here.
Thank you, Ayse. Brian, next question is going to you. And just a note on the panel, we're going to go until about 10:40. And I'm going to finish out the first 10 minutes of the panel, just sort of setting the stage with the panelists, and then we'll move to questions from the audience. So, Mads, I remember when we were on the bus in Denmark, we calculated the number of order of magnitudes between the work that you're thinking about and the work that we were thinking about in paper 1. And there's somewhere between 7 and 9 orders of magnitude between those two ways of thinking. And so I think the idea, what I love about paper 1 and paper 2, is that they come at the same problem from two completely different perspectives. The idea that we're sort of building a bridge between these two areas. And so I wanted to ask Brian to comment on that, and to sort of also comment on the role of power plants in the future, and sort of how does someone in the audience reconcile the ideas that are being developed in paper 2 with the magnitudes in paper 1.
Thank you, Eric, and thank you for some nice comments. I really appreciate it. So, I mean, there's a lot of discussion points that you opened up. So I think I'll choose 2 things to focus on. Is it me that's doing this? Oh, okay. This one thing is the data centers and this conventional demand we have, and the expectation that everything can become flexible of the existing demand. I do not believe this is possible. You can induce some flexibility for the existing demand, but it's also hard. There are some structural, what I would call conventional electricity demands, or structural electricity demands. And in my mind, the data center comes under this. And then on top of this, we have the flexible demands, which are individual heat pumps, which could be like electric vehicles. And of course, in the future, you can also induce something on data centers if they have like a regional storage. You'll have electrolyzers. So there are some distinctions between what is flexible and what is not flexible. And I think we are not completely aligned, the authors here, about how much that is, but I think we can agree that there is some level of constant, some level of flexibility. And when we know that, then we can talk about how to regulate. And one thing that's being done, for example, is that if you want to build a new facility, you will have a capacity put to you. You can use this capacity. You can't go beyond this capacity. That's a you can call it regulation. We can also just call it common sense, that we can't build a line that is infinitive for a data center. So what does that mean? That means, in my opinion, that when we integrate renewables, we have to acknowledge that there are some structural constant electricity demands, and most data centers come under this. And that means we need some power plants that are flexible to operate at those times where we do not have wind power or solar PV. What type of power plants are they? They're certainly not base load. So everybody that says base load does not understand the future energy system. Not at all. But they're peaker plants. They're peaker plants, you could call it, if you want to use a conventional word for these kind of things. I would call them flexible market players that are able to step in those in the future 10 to 20% of the time, where we will have a deficit of wind and solar. In some literature, they call it Dunkelflaute, when it is not happening. So maybe some people know that term, but it's about those 14 days where it's really cold. There's a lot of electricity demand, and we need some power plants that step in. So I think we need to have that conversation, that we need to expel the coal, but we need some peaker power plants that can step in with biomethane or some other substance. And then we can there's a role for batteries, there's a role for flexibility, but batteries will not balance the grid for those 14 days that it's really cold and where we still have the structural demands that we cannot shut off. So that would be my comment. Yeah.
Thank you, Brian. And then we'll just go to Mads for comment from you, opening comment, and Henrik, and we'll move to questions from the audience.
Comment on many good comments. So it's I mean that there's open questions around grid capacity. How do you measure it? What is the right value to place on grid capacity? There are questions around, are data centers flexible and at what price? And so then there's a question around what incentives do we need to send? There's a question on reliability and resilience have been measured in the past based on worst case outages, N-1 contingencies, N-11 contingencies. What is a contingency when a wind farm does not produce wind? Is that an N-1 or N-1/2? And so there's a lot of open questions around how do we measure resilience of these new grids, whether they're transmission or distribution. And so I would place the comment on how do we measure resilience, how do we value it, and how do we provide it as a service. And I think the future grid will be heavily dependent on resources that can provide resilience and reliability as a service and at some cost. And that may be that 10 or 15% of peaker plants that sit and wait, and they are paid for that service. They provide the reliability, but otherwise flexibility and renewables handle the rest. And so I think those are going to be interesting products to understand and study. And I think the grid physics itself will play a big role in defining those products.
Yeah, thanks a lot for all the comments, and I basically agree with all of you. I think that if we should continue discussions, maybe taking data centers as an example, we are working with the big players in the data centers, Google, Microsoft, Meta, and so on. We have some upcoming large project, and I'm so happy that you came today because I hope we'll find some time to discuss this in further detail. What we can see, for instance, is that you talked about energy efficiency. It's right that the consumption of the chips and so on has increased. So if you really look into that, but it's also a fact that we have. I don't have the actual numbers, but I wrote a paper a couple of years ago with some leading energy providers that out of around 62 data centers in Denmark, we only use the excess heat or the cooling heat in 3 cases. Maybe Brian has more. And we live in a cold climate. And so we can make the entire system much more efficient by using this heat from the data centers. And then we also just last week had meetings with our TSO, which have, because of this removement or stopping these combined heat and power plants, they need more balancing services, fast responses. And data centers can definitely provide this, but because the way they build data centers offers this possibility in most cases. Typically, they don't build just one data center, but in a triangle to be reliable. And so they can move some loads around, depending, of course, of the job. Another thing we also focus on in this the new upcoming projects, which I would like to discuss with you and many of you also, is that it's not only the hyperscale data center. I think the tendency is that we'll have more medium scale and maybe also edge data centers. So the upcoming work and the projects we are looking at will actually, we have Google, Microsoft, and Meta in, and we have some European companies like Danfoss, Fraunhofer, and Schneider, for instance. But we will zoom in also on the edge data centers, which will play a big role, and they can definitely also provide the flexibility. So we have a lot of challenge. I fully agree. I fully agree on what has been said, but I also, maybe I'm just too optimistic. I think there are some possibilities. We have one case where we saved around 85% of the CO2 emission by a flexible operation of a data center. Yeah, I can tell you about the case.
Thank you, Henrik. We'll move now to questions from the floor. When you ask the question, I'll repeat it for the folks online so they can hear it through the microphones. So yes, sir.
So, hi there. So I introduce myself as well, or
Please.
okay, I'm selling analog devices, electrical engineer. I have a question about the premise of the second talk. So kind of we're introducing new elements into distribution, having all these additional control elements. And presumably the premise of this is to equal economic value and efficiency by setting up these structures. So now I want to ask, what is the value of these structures if, as in America, in New England in particular, the cost of generation, the cost of distribution place assets represent a 3 to 4 times price premium relative to wholesale. And that the only reason these resources get built in the first place is because of programs like Massachusetts Smart, like Eversource, having the rate payer from $250, $500 a kilowatt, which is substantially more expensive than the transmission level interconnections. And the only reason that it makes sense to do this is because someone building a community forest solar farm is going to get recouped through a premium there. So if this is a compensation structure that you've set up already to encourage these things to be built, what is the notion of market to increase efficiency in the first place? So where's the value there? Because these things have to be in. Like these things already be paid 3, 4, 5 times market value. And so it's like how is this going to be beneficial to the consumer if you set it up this way?
Okay, thank you very much. Excellent question. I'll do my best to recap it. I won't succeed, but I know the panelists have heard it and people will hear the answers. So the question is about paper 2, there are new architectures being set up at the distribution scale. And what is the economics of those, understanding that a lot of that is being subsidized by policy right now? And what is the future of that? Is that an adequate summary of that? So I'll turn that over to Henrik and Madsen.
But if I should maybe focus in on the situation in Denmark and Europe, I think, as we also wrote in paper 2, one of the challenges, the major challenges are the regulatory framework. I agree with you that today we have the tariff is very, very high, and it's not intelligent. So we have paid for the infrastructure. I think Brian knows the number, but in my view, we have paid way too much for the infrastructure. And we need to have more intelligent tariffs to have the cost down. Also because then we can more easily see when we have green power and black power and can get a price signal for the demand response. So there are some technical challenges as Mass and clearly outlined, but I definitely think that are also regulatory challenges. And on top of the tariffs, we have also high energy taxes, which are just constant, which removes the signal. So, but Mads, you can probably help me.
So thank you for starting off with such a nice, simple question. This is a question we often discuss. And so in my mind, there are kind of 2 paths to decarbonize. There's the big grid solution, where you build out capacity on transmission. You maybe replace coal, gas with nuclear, solar, wind at scale, gigawatt scale. You need to build transmission. And until I see someone, put down 10 years of patience and $10 billion, I don't see transmission being built quickly enough. And so then the question is, how do we move forward with decarbonizing if I have to wait a decade or 2 to maybe get a transmission solution? And so what I think you're seeing is that policymakers are responding to the sprinting part of the decarbonization cycle and saying, how can we decarbonize if we are not transmission operators? And so I think states are moving forward with incentives which may not be ideal and certainly are not final, but are trying to, and I think what has happened in the last decade or 2 has been they've wrapped all of these goals of decarbonization into a volumetric charge. And so you have these weird incentives, which don't really reflect true costs, and they don't really reflect the impact on the grid, but they're a way to speed up things. And if you speed up things, you learn. Sometimes you fail, but if you learn faster than you fail, you're succeeding. And so what I think we're seeing is that all of these, what do we call it, utilities, all these territories are learning from the experiments. And I think the experiments are changing. And so a lot of the things we discuss online sometimes around tariffs, demand charges, dollars per kilowatt, which is far more reflective, I think, of grid capacity, is something that probably will be reflected soon. And so that volumetric charge has limitations. And so I think what we need to see is more of the cost of capacity being reflected in the cost of deploying resources. And so my guess is that utilities in the US will probably start to mirror what we're seeing in Australia around pricing distributed resources as a capacity limit with a capacity cost that's fixed, because that makes the economics work. And then I think you'll end up with different optimization and control algorithms that will reflect managing demand, which in Spain is what they're doing when residential consumers have demand charges. So I think it's a very interesting question. I think that dollars per kilowatt will be part of the solution. And I think that'll equalize a lot of the problems. And give me 10 years and 10 billion and we'll solve transmission. I just don't see that one. And so then I think the question is, if we are looking at a bottom-up solution, a distributed solution, what value can data play? What should the electronics be? Right? Analog devices makes electronic devices. What should these devices be sampling, measuring to help make better decisions about regulatory tools and methods? So I think it's dollars per kilowatt is probably the shortest answer.
Just quickly, you really hit on a tender spot, and that is to say, I think we're in some danger of consumer revolt, as we've said to homeowners in particular, business owners, this is the pathway. And we're hearing stories about people, okay, I've spent the money to put in heat pumps and my electricity, already high electricity bills have gone through the roof. When in fact, you obviously need to do a holistic approach, make sure that they're looking at insulation and windows and as well as demand side kind of and pricing kind of advantages. So I think it's timely to take a fresh look at all these various charges and policies that are related. Bills are so complex. I mean, I live in this world and I have trouble reading my bill and understanding what all the relevant charges are. So we need to simplify and we really need to be true to our promise. So it has been, I love, Madge, you're drawing the picture of how iterative this has been. The utilities and the policymakers kind of feeling their way, all those various charges on our utility bills, each one of them had a reason, had a rationale, but they weren't, as we're adding each one, we weren't necessarily looking how they're interconnecting with everything else and whether something could be taken off. So I love the question.
Ayse, did you have a response as well? Okay, well, we have time for one more question, then we'll get a response and we'll wrap up this session.
Matt,
yes,
your story here at MIT and the Climate Policy Center. Gelen mentioned the value of the cross-cultural exchange that Kanzi provides, which I 100% agree with. Both papers appeal to a common language going forward. Eric, you made the point that we need hundreds of millions of people on board if we're going to do the transition. So I have a suggestion and I'm asking for a response. If we could come up with a better way of describing in paper 2 what you call control, because at least in the US, like the word control is radioactive. It goes against US culture of autonomy. Like, don't touch my thermostat. Don't drain my EV battery while it's charging in my garage overnight. Don't pull power out of my Tesla Powerwall. But how else could we frame or use language that's accurate, but not as scary culturally as control? Because somebody else is going to control my electricity, my energy, my power.
I don't have a solution, but I would add another word, like regulation. I mentioned when I was speaking, like when you say, you need regulation, people are like, oh, let me get out of here. I mean, it is regulation at the end. Like we need some harmonized design of these things as opposed to the individual power consumer, and the grid is supposed to just magically provide all this capacity and transmission, etc. But I don't have a solution yet, but I like the thinking that, can we get away from control and regulation and present it in some other way?
Thanks a lot, Drew. I think that's really important. I just realized now that this was a big mistake to call it control. But and what we also write in the papers is that we should try to ensure that the end users are in control, so they are taking the decision. And of course, we should discuss. Maybe we should change it to hierarchy of automations or things like that. I think that's more appealing to the thinking, positive thinking. But thanks for this.
Go to Brian.
You can take the man. You can take me out of IEEE, but you can't take IEEE out of me.
Maybe a technical standard would be a term that could be more, and then you have the market on top or something like that. But I was just thinking of what you asked and what you answered, and then I tried to reflect upon that in the European case. And maybe we can discuss that also in the afternoon about the future collaboration. But I would just like to remind us that this, maybe some of you know the Desertec project, which was this, I call them physicists that look out the window every 10 years. And then they think, why not build a cable to Sahara and do some PV and then take that to Germany? And it's a physicist fantasy. It's not a real life solution. And it just dawned on me when you asked the question, and remember the maps that we saw at the MIT CIPRA workshop the other day, that maybe we need to try in the Kenzie project to quantify some of this, where we go more local, and we are not trying to transmission solar PV from the west to the east, or trying to always build the wind power where it's cheapest, but try actually to understand that there's a localized source that we need to use first, and that we actually need to limit this transmission line problem, because in Europe, we're not talking about interconnection from Spain to Finland. And if we put a map of Europe on top of the state, it seems that that's what you're doing. And that is completely, I mean, economically not viable. It's not in Europe, and I suspect the laws of physics are not that different here, so I wouldn't expect the land is cheaper, but the copper is not. So,
all right. I'd love to thank our panel and thank the audience for the wonderful engagement.
Thank you. That was the first half of the seminar. We'll have a break now. I think we'll cut it to 15 minutes, so we will meet here at 11:05.
Thank you very much. And so I will do my best to present to you the findings that we had in the study, and I just put all the co-authors from DTU, from MIT, from Orla University and Tufts, where we've been comparing kind of the road forward for hydrogen and what is the role of hydrogen in future mobility in the EU and the US. Are we going down the same path? So what we've been focusing on the hydrogen plants and the expected use of hydrogen, how we expect it to be used, and also about risks that have been not storage, and finally policy measures. So everything that we have numbers and tables, but we don't have to discuss them. I will go through the basic points of them. But if we go into specific scenarios, summarized from consistent ADCs that we do in the US, and then there's our own studies, the new cohort, the study and then some from the university as well. And one of the points of this is what we're going to use the MassCEC in terms of the uses of hydrogen. And we can agree across many of the
scenarios, particularly those with the high share of renewables in, that green fuels is really one of the main points of use. And another point is for industry, maybe for transport and trucks and ferries and so on. And another point where we also see some correlation is that we see that in terms of backup power, we might need some, but the amount of hydrogen we're going to need for that is not going to be huge. So we're going to maybe use hydrogen for backup power, but only in limited amounts and only in the few hours where it's really needed, because of course the efficiency of going power to X to power is not that good. So this was some of the findings on the demand side. Then comparing on the production side, it does look a bit different. We see in the beginning in the US some steam methane reforming and what we call gray hydrogen, where we don't capture the carbon. And then we see across some of the scenarios also some blue hydrogen. In our case, in the EU34 study, this was kind of in the beginning, it could be economically feasible, and then you get a lock-in and you kind of, it carries through because you did the investments. Where there's some also thermal reforming in the US studies. But across the plane, again, we see a lot of electrolysis, again, particularly in the scenarios where we have high shares of renewables. And then, interestingly, in the Princeton study, they talk about bioenergy CCS hydrogen. This is not discussed in Europe. So bioenergy CCS hydrogen relies on either synthetic gas from thermal gasification of biomass or biomethane being cracked, the carbon captured and put in the ground. And this is not really what we envision in a European context. And I think that has to do with the fact that we are discussing a lot about sustainable levels of biomass use for energy. So what we are talking about is the need for carbon management to keep the carbon. If we have green carbon, using it for maybe liquid fuels for aviation and shipping. So the problem kind of changes if we take into consideration the full picture. Then when it comes to production capacities, we do see a lot of electrolysis, green or pink, through the system. And this links to, and I can't show it you here, but if we do the calculation and look at what does the capacity mean in terms of how much we produce, we end up with the electrolysis lying in the number of 3,000 to 5,000 full load hours per year, which means they are only running half of the time, broadly speaking. And this is pretty consistent across the studies. And what this means is that it's really important to look into flexible use of hydrogen. It links nicely to, let's say, wind having a capacity factor of 50%, which means that 50% of the time we have a lot of green electrons in the system that we can capture in our electrolysis units and use to produce hydrogen. But as also pointed out by Tobias and others in the paper, we need to make sure that this doesn't affect the lifetime of the electrolysis units, that they are operated flexibly. We need to ensure that we still get a nice long lifetime of the units, although we operate them flexibly. Tobias is nodding, and I hope all of you kind of, whenever I'm trying to fairly tell what you contributed with, you will break in and say, well, I actually meant this or that. In terms of infrastructure capacities, which is also the reason why we added the ADP study for the US, to compare with some of what we see in EU, we've looked quite a lot at this. I think what is important to take away from this is that we are expecting to see more grid capacity in a European context, maybe than what is expected in the US. In the EU, we discuss a lot repurposing of existing natural gas pipes for hydrogen. As I've followed the debate in the US, there's less appetite on that here due to the conditions of the current natural gas grids. But what we can see is that hydrogen grids can alleviate the capacities needed for electricity transmission. So there's kind of a trade-off, a competition, or nice supplemental status of these different infrastructures. So let's go to, these are kind of the long-term plans, right? And they differ a little bit in terms of maybe having more reliance on blue hydrogen in the US than in the EU. But let's see what's really happening at the moment. So we took some numbers from the IEA, and what we can see is that the plans that are in the works is a lot of electrolysis, production of the 33 million tons are the plans that are in the books, if you can say that, or in the pipeline. And in the US, it's half. And you can see that the share of natural gas based is high, but still the share of electrolysis based is also really high. If we then look at what is happening, what are the final investment decisions made, the picture is, first of all, you could see it's kind of a lot lower number where we actually are. So we were planning for 33 million ton in the EU, and we are now at FID on 1.5. In the US, it was 60 million ton, and it's down to around 1 million ton. And where does that come from? In the EU, it's oil with CCUS. In the US, it's natural gas with CCUS. It's not that much electrolysis currently. And this is in opposition to what's happening in China. They are also going on with their plans. They have similar FIDs, but that is mainly electrolysis. So they're implementing currently much more than we are. Just illustrating, we may be losing the race to China when it comes, both of us. So what are they planned to be used for in the EU industry? Ammonia and refining. These are the near-term plans, right? And for the US, a lot of ammonia, some injections into the grid. It's also not so discussed in the EU at the moment. This was the hype at the moment, kind of saying, let's take hydrogen and put into the methane grid. But a lot of people are like, no, these are two high quality gases. We should not mix them into a lower quality gas, because it also has a lot of implications on the appliances and how well they use. And interestingly, you actually have a higher methane slip. If you have a gas boiler, you get a higher methane slip if you add hydrogen into the mixture, and the boiler is not really meant to be used for these mixtures. So in EU, plans are industry, ammonia, refining. In the US, plans are ammonia and injection into the grid. Also some alternative fuels on both sides. But where are we today? In the EU, refining industry. In the US, ammonia, refining, a little bit of mobility. So we're just constantly behind where we want to go. And also, yeah, this is kind of a crazy chart, and there's some data missing, but it's just to illustrate, for example, for EU, right? And to illustrate the ramping up that this would require to put all those plans in effect, right? And you cannot kind of quote me on this graph because there's data missing and stuff, but it does illustrate a point, which is the ramping of these things, the sizes of the ramping is insane. And which means we need to get started. Even if we want this implemented by 2050, we just need to get started to get these value chains up and running, and the regulation and everything else, so that we can get there. In terms of the flexible operation of the electrolyzers, questioning kind of, are they fast enough? It seems that they can be pretty fast in ramping up and down. You can see particularly the PEM ramping up and down in a few seconds. Do they break? It's not really clear. We need to look into the degradation if we have a flexible operation. Also, I think depends on whether we are running in a hot idle state when we are not operating them. But basically, we need more research. So how much can you change? Also quite significant changes possible. And is it profitable? Well, this really depends a lot on the electricity prices, right? And but one point that could make it more profitable is if we can kind of tap into some of the balancing markets and provide ancillary services with flexible operation of our electrolysis units. There has been studies, and this is a study from a thesis, which looked into what is the impact of the transmission expansion on hydrogen capacities, and looking at different cases. This is also kind of with data from the Princeton study, but where we look at if we have a power system alone, if we allow for hydrogen into the grid as well, and if this hydrogen, so this is it's including the hydrogen demand, and then we say, okay, what if we also allow for CCS, direct air capture, and the likes, and the final one we then add this bio-CCS option. And what we see is that the capacities decrease with the more options you get, but they kind of increase with the slightly with the amount of transmission expansion. So illustrating that as an electrolysis owner, you get access to more renewable electricity, to more cheap electricity when the grid expands. We looked into Power-to-X policies. A colleague of mine, Claire Birgensley, and her PhD student from RTE, and they compared the two regulatory frameworks and associated support schemes that have been or are planned to be implemented in the EU and in the US. And what is really different is that the IRA has some definitions of clean hydrogen. And if you can meet these requirements, you are guaranteed that you will receive a certain subsidy. Whereas in the EU, we have a limited amount, so they offer out auctions. And if you win the auction, you get the price you bid with. But if you don't win the auction, you're just on your own, right? And we've seen this in the wind turbine market. We've seen how this stop and go policy can kind of hamper a little bit the development of a brand new industry. So some of the conclusions are kind of that maybe this maybe the US way of doing things is going to allow for a much faster ramp up of the hydrogen industry. So some of I think that we could say that there are similar ideas about the emission intensity levels. One difference is that when it comes to the renewable content, we have this renewable fuel of non-biological origin that governs the what is green hydrogen, and there it's not okay to rely on biomass for the production of electricity for green hydrogen. So we are simply maybe more concerned about using a lot of biomass in our future energy systems that maybe is the case in the US. When it comes to how this then is implemented, you can see that at the latest auction, we had a cap on 4.5 euro per kilo hydrogen for the first auction and 4 for the next. And actually, the mean successful bid was down at 0.44 euro per kilo hydrogen. But then you can top this with the selling the hydrogen certified, so the certificates. Whereas in the IRA, you get different subsidies depending on what the emission intensity is. And I think that sums. For both in the EU and the US, there's this focus on additionality, on temporal correlation, and on geographical correlation, which is very important. And one of the things discussed is this temporal correlation, because in the EU, we're starting with a very lax temporal correlation and then expecting to have it more and more on an hourly level. Okay, I'll wrap up now. So the conclusions on the level of the plans is that there are many plans and much less projects with FID, 15 times less in FID than which is planned, both in the EU and the US, with a very steep ramping curve. When it comes to where we are with FID, actually EU and US and China are at a similar level, but the current projects in the EU and the US rely on fossil fuels while China is looking at electrolysis. EU and China in the future mainly plans for electrolysis, while the US seems to have plans to continue with the natural gas, with the CCS. In China and the US, the main use today is on ammonia, and in EU it's refining. And future coming projects in the EU are both industry, refining, and ammonia. We think that electrolysis is the way everybody wants to go going forward, but it needs to be flexibly operated. And what we can see is that power transmission, CCS, and this option of BECCS hydrogen will have an impact on the electrolysis levels needed. We have pretty similar policies, but with some important differences in the EU and the US. Particularly the IRA may reduce this risk of investors and facilitate this nascent industry, while the EU auctions allow a tight control with the resources spent. So of course, there's a reason we're doing this, but the question is it now? We should do it already. And then ending up with the discussion on further research, which will be the topic after lunch for the CANC members, but I'm happy to hear your suggestions. We think we need to look into what is really going to be the future hydrogen demands, because there's a strong competition with electrification, of course, and other. We need to look into this flexible operation of electrolyzers. We should have a good look at the environmental impact of policies and operation. One example I mentioned was the temporal correlation, which matters a lot. And of course, the additionality. And we think that it's important to see this across different sectors and co-optimize across the different sectors. And there I mean electricity, I mean hydrogen, I do mean district heating, or even individual heating, but kind of looking at what we need in order to integrate large shares of renewable energy is flexibility in the whole system. So this is, of course, transmission, both of electricity and hydrogen, etc. It is the possibility to have flexible production of electricity. It's the storages, and as Gelen mentioned, it's very much the flexible demand as well. And then, what is the impact of limited sustainable biomass and CCUS options on hydrogen production is a question mark. Where we gonna, if we capture green carbon, biogenic carbon, are we gonna inject it into the ground to get negative emissions, or are we gonna use it for green fuels? Yeah, so these are some of the suggestions of things we could look at together, but there may be many more, and I welcome your suggestions.
Thank you, Marie. And then the last speaker, or presenter, I would say, will be done by Elizabeth Wilson from Dartmouth College. And while we are changing, because Elizabeth wanted her presentation to be like a fish dinner, it should only be served fresh, meaning that it was not sent beforehand. It was just made. So, well, Elizabeth is the distinguished scholar in environmental studies and public policy, and she is also the person who have made sure that we all had a smile on our lips in the cancer group with her never failing good mood. Professor Wilson research focusing on energy policy, system transformation, and societal implication of the green transition to clean energy. The work explores the intersection between technology, institution, and policy to create pathway for sustainable energy solutions.
Okay, that's enough.
Okay, you take it from here.
Yeah. One of the things that I have really appreciated about working with the Kanzi group is the opportunity to really think about the sector from a global perspective. So my interest is offshore wind sector globally. And what I'm focusing on with my colleagues in Taiwan and Australia and Denmark and the UK are really what some of the challenges are. Today, I'm going to be talking about institutional learning and how that is evolving within the US sector. The reason we're focusing on this is that I often have colleagues that say, well, we can't do this because we've never done it before. And that's ridiculous because we do things that we have never done before all the time. And so what we've been trying to track in this paper that I'll go through are ways that the US institutional infrastructures and our regulatory environment has evolved to adapt to the demands that are buffeting the offshore wind sector. And this audience is great because you already know that there's 75 gigawatts deployed globally, half in China, most of the rest in Europe, and other places in the world where we're starting. So the year I spent at DTU Wind, 2022, I was in Denmark, but I got to visit Vietnam and Taiwan and the Philippines and Australia to really understand what some of the challenges are. And when we're thinking about offshore wind, I think about it as a mega project. There's a whole academic literature on mega projects. The Big Dig here in Boston was a mega project. Mega projects, as you know, are billions of dollars. They're at scale, gigawatt level scale in the energy sector. And like all mega projects, they're usually late, they're politically contentious, and they're always over budget. So that also tracks pretty well. Building mega projects is hard. And it's not only hard in the US. I wore my Where's Waldo shirt, my Danish Where's Waldo shirt today, because as you know, the Danish energy offshore wind auction came back with 0 bidders. But they're also hard, this is for the Danes in the audience, in Sweden. Every Dane likes to see Sweden failing at something, and here is Sweden canceling their offshore wind projects over defense concerns. They thought it was too dangerous in the Baltic. I found this justification actually very interesting because in Taiwan, they looked at offshore wind as a great technology because it was an extension of their defense capabilities of the island. And we've heard the same arguments happen in Poland, right? So I guess where you sit is where you stand, whether or not you're pushing this. So this is for my Danish friends. The shirt is for you guys too. And I think when we're talking about offshore wind in the US, it's just useful. because people paint our policy environment, our 30 gigawatts by 2030 goal and future pathways as if it were all the same. And I always point out to my students and others who aren't as familiar that it's the yellow part of the US where we can do the fixed bottom turbines that are what we've deployed around the world. Those are up to about 60 meters depth of water. So this really is an East Coast play now. And when I talked to my friend at the California Energy Commission, I'm like, how did you guys sign that goal? Because those guys are all floaters, right? That technology is not yet ready. So the action is here. The action is in the East Coast. The action is with our fixed bottom foundation. And it's really hard. So the institutional challenge in figuring out how the development goes has been really encountering the permitting complexity and looking at the cumulative impacts. And so when I'm thinking about how to build an offshore wind farm, you're first looking at securing the lease area. And the learning within BOEM of taking hypothetical areas and then asking for comments and scaling it down and down and down to do the lease has been well tracked up along the East Coast. Running the regulatory maze. I have been told that I need to be more positive. So the way I'm presenting this is that offshore wind provides a great opportunity to meet lots of regulators. Swipe left, swipe right. But basically you can meet them all if you decide to build an offshore wind project and become relatively good friends with them up and down the eastern seaboard. That said, in a state like Massachusetts or New York or New Jersey, there's a lot more people involved in this process. When I talked to the regulator down in North Carolina, she's 1 and she's 0.7 on offshore wind. So the institutional capacities along our East Coast states are very, very different. Then you, of course, secure funding, build, and connect to grid. Estimated time with our first 2 projects around 15 years. So this is also typical of mega projects taking a long time. But as you know, and as we've seen, the exogenous risk, interest rates, supply chains, other things happening like a war in Russia can really affect your cost and planning. And so of the projects in the US, the 26, 16 have either walked or they've renegotiated their contracts. And projects are more expensive and very, very hard. And we've seen this in the media again and again. But today I want to focus on something a little bit farther along, and that's connecting to the grid. And I first got interested in this because I've done onshore renewables for years and looked at transmission planning for years. And the way I think about transmission planning is as a blood sport. The planning's easy, actually, it's the cost allocation that's hard. And I remember American Electric Power years ago having a beautiful map of the US with high voltage power lines drawn across the country. And I was sitting next to a grid planner who elbowed me and said, yeah, that's what you do if you're a kindergartner with a bunch of crayons. Because actually building the grid, getting the cost allocation, figuring out how to allocate risk across those projects is exceptionally hard. And anyone who's tried to do transmission planning knows this, as evidenced again by the New York line that was canceled 3 days ago. Thanks, Mass. So as we're thinking about evolving toward, it's what? No, you pointed it out to me. So as we're thinking about this, in the policy world, we often say that the scale of your solution should match the scale of your problem. And with offshore wind, our first project by project area is really moving to more regional approaches and regional learning within our institutions, as evidenced by the solicitation that involved Massachusetts, Connecticut, Rhode Island, as evidenced by the Fishermen's Compensation Fund that's stretching across the East Coast, and as evidenced by what I'm going to share with you today, some of the transmission activities. So the 3 things that we're looking at in the paper, I have a draft academic paper that I didn't share with this crowd, but I shared with the CANSI members. If anyone else wants it, I would love your comments on it. But we're looking at 3 case studies, multi-state by state procurement, seeing how the solicitations have changed to address the exogenous risks of offshore wind, the project from project by project to standardized fisheries compensation. And then what I'll talk about today, the conversation that would take us from point to point of injection to a coordinated grid integration. And I think this is really interesting, just from images that are, available online, from the status quo where we have individual projects and individual cables to a more coordinated approach where you have a backbone or meshed infrastructure, these reduce the number of beach crossings, which we know are points of contention. Has anyone tried to build a transmission line in the Hamptons lately? No, you haven't, because you can't. And you appreciate that it reduces the cabling by 35%, so your environmental impacts are down. There's lots of great reasons that we know from the beginning of why we should be doing coordinated transmission planning for offshore wind. Happily, they're having the same conversations in Europe. The first I found was from 2005, a Dutch report that talked about the need for coordinated transmission planning for offshore wind. And like Mass, I have a secret paper, but only mine is from 2006, that really highlights that we have been talking about coordinated transmission for offshore wind for a long time. And I want to highlight this one sentence here. Governmental support will be needed to start initiatives on this. After a lot of analysis, the researchers determined that it wasn't in the interest of the individual developer or the TSO to put in the extra resources to secure the benefits that offshore wind coordinated transmission would provide. In the US, we have a similar example. I mean, how many, you're not like my students. How many of you guys remember the Atlantic Wind Connection? Okay, about 3 of us, but this was a Google proposed line in 2010 that was going to connect down here from Virginia up to New Jersey. I spent a lot of time over the summer reading that original FERC docket. And what I appreciated was that the argumentation against this line is exactly the same as the argumentation against these lines today. So some things, the more they change, the more they stay the same. So there's a lot of literature in Europe, in the US, on the need for transmission. And when I explain it to students, an HVDC multi-terminal is kind of like this, and not like this, or because it's the holiday season, National Lampoon's Christmas Vacation. And so when I'm thinking about the Offshore Regulatory Challenge Transmission Edition, I'm looking at meeting this 85 plus gigawatt target, as we talk about in the US study. But I'm also then thinking about these mega projects spanning not only state jurisdictions, but different regional transmission organization. When you explain the RTO infrastructure and rulemaking process to a European, they look at you first very in a puzzled way, and then they wonder why you're doing it that way. And you just say, because we are. But really connecting ISO New England, New York ISO, PJM, and then the Southeast is pretty hard. The mega projects spanning these jurisdictions with different decision bodies. So I just want to highlight then some of these elements here. As I said before, coordinating transmission saves costs. It will create values. It will reduce curtailments. It will reduce the environmental impacts. It will reduce impacts to fishing communities. It will reduce those beach crossings, as I said before. And it could also shift developer risk. Some of the earliest projects like Empire 1 and 2 have been very delayed because of their difficulty in getting those transmission point of injection approvals. So it's expensive to construct. Current policies do not support it. And like all transmission projects, cost allocation is very, very hard. So to start to understand how we're thinking about offshore wind, we focused on a case study of New Jersey, and appreciated that New Jersey and PJM have been in this conversation as long as anyone. I think New Jersey is an interesting case study for several reasons, not only for their strong offshore wind goals, but also because they have from the very beginning mentioned transmission in their solicitations. And the first ocean wind project was evaluated favorably because with the developer, they had identified where they're going to put it. None of the other projects had, but they'd identified that point of injection into the grid. And from the very beginning, they have started to work with PJM and identify with an RTEP study, a regional transmission planning study, where those points of injection could be and what those implications are. And so the study that they had and the evaluation of some of these solicitations imagined how this could work out and what the different options would be. And so in 2019, they were giving extra points in their solicitation for a readiness criteria for project viability. By 2020, the Board of Public Utilities with PJM coordinated the different transmission possibilities up and above. That was that Brattle report that evaluated all of those different projects. By 2022, the state agreement approach, this is an innovative policy they developed, took on 80 proposals for 13 different bidders to construct onshore cable vaults and duct banks to allow for the readiness of offshore wind infrastructure development. So you, the developer, would still be building there, but those points of injection are going to be ready. And today there's an ongoing pre-build solicitation to fund these cable vaults and duct banks. So New Jersey, and this will be 4 offshore wind projects that are going into one. I know you guys went to offshore wind or to Vineyard yesterday, but that Barnstable project is the subject of many papers. And how do you feel about this and the political contention? It's hard. So this is a state level. There are also New England level efforts, but I think one of the more interesting ones, and Eric knows a lot about this as well, is of course in March, you were all waiting like I was for the offshore wind development in the Atlantic region and the transmission study. And this is a US NREL report, and we'll have Brian on our panel later to talk about this, but where they identify all of the ISO New England, NISO, PJM, Carolinas, potential points of injection. And what they appreciate is that meeting the goals require coordinated transmission planning. Now, my question is this just crayon lines on a map? Is this something we'll be able to do? What will we need to be able to do to pull this together? And so one of the things we talk about, I have a 5-step plan. I'm only sharing step 2 with you. Talk to me later if you want the other 4. Is pick a venue. And so how are you thinking then about this institutional home for offshore wind? What should the RTO and FERC roles be? And right now, I don't know how many of you follow, but the Northeast states have a collaboration, and the MOU was signed this summer to enhance the coordination of offshore wind transmission in the US. So the conversation is happening now. And the first job is going to be to pick a technology standard. The Grid Deployment Office, which under Project 2025 is axed, but just put out this solicitation to put together and hopefully fund that consortium to begin this work, $1.25 million. I'm hoping the Hopkins Group gets it. Okay. What are the main barriers of building coordinated transmission? I just want to highlight that it has been a good idea for many decades, and it is very, very hard. Of the offshore wind projects we have, and I know that this is a technology under risk, 10 have completed environmental review and permitting, and under by after these a couple of plastic. This work that we've been doing has really tried to focus on understanding how our institutions are evolving in response to the needs of a sector populated by mega projects. And I gave you the transmission case today, but as we're thinking through the problems, and I was listening to the talks earlier, I would love a conversation with all of us during the discussion of how we can fit the size of our solutions to the capabilities of our institutions. Because I am actually worried that the type of solutions we're proposing here are not going to be supported by our institutional decision-making, funding structures, and ability to put this together. And so maybe Mass's version of the grid that is more decentralized ends up playing a role, not because it's a better technological solution, not because it makes any more sense than this, but because we live in a country today where our institutions can't support this level of coordinated decision-making. If we were in China, I think this would be a great solution. They've built a high-speed rail network in 5 years. They've put in new transmission lines all over the country. But I don't think in New England 2024, we live in that world. And I would just love to think with you more about where and how our solutions make sense for the problems we're trying to solve and what is possible. Don't let the perfect be the enemy of the good. Don't let our ideal solutions of how the world should work interfere with how it does. So this is the great people I get to work with on this. We've been having a really good time poking into offshore wind around the world and thinking about how we make sense of these 1.2 million pages of documentation we've created for an almost imaginary sector, with the exception of Vineyard and South Fork and the others. So thank you very much for your time, everyone. We have our session. And now we have, I'd like to invite everybody up to the front who's part of, we have a, yeah. And I think, Brian, you're coming up too, and Marie and are coming up. Great. Should I take this off? So I'm going to start this off. Do you guys want to make a few comments first? We're going to go ahead with that. And introduce yourself.
No, you can go first, Brian. Okay. Hey, everyone. Brian Sergi. I'm at the National Renewable Energy Laboratory. I work mostly in capacity expansion modeling for particularly the power sector. So a lot of my comments are probably going to be grid oriented. I guess let's start Marie's paper on the hydrogen work. Covered a lot of really interesting things. One policy thing I think I want to flag just for discussion that I don't think we talked about in the paper, and is that one thing I'm hearing a lot is that challenge, at least in the US, I don't know what the situation in Europe is that electrolyzers, as large industrial loads aren't necessarily able to access wholesale like electricity prices, which would be lower and potentially time varying. So you could take advantage of periods of like high wind and solar where the grid price is very low and running your electrolyzers then and then turn them off when things are high. So just some feedback we've been hearing from people looking to develop projects and some of the modeling group is that, even the generous support with 45V doesn't get you as far as maybe you want it to if those loads, those electrolyzers aren't able to kind of capture the value of charging or running the electrolysis when you have a lot of abundant wind and solar and the electricity is very cheap. So I think that's something that would be interesting to kind of poke at a little bit here from a policy perspective. Then the other thing I think I wanted to highlight, you captured this really well. There's a lot of uncertainty in the hydrogen demand from kind of all the sectors. I think it'd be really great to try to capture some of those ranges. And to me, that emphasizes the need for, like you said, more coupled modeling going forward, but also just a lot of emphasis on kind of scenarios that look at competition between electrification or other solutions. Many of those are kind of nascent and emerging, so we don't really know how they're going to take off. And I think trying to parameterize and capture that uncertainty and provide ranges for the demands is going to be really important. And then one last piece I wanted to pick up on is just, again, I come from the power sector side, so I think about it a lot. You mentioned that hydrogen is probably going to play a really small role in the kind of power sector compared to, industrial or other demands. And I think that's probably true, but I don't want to discount it. I think it's a very important role in the power sector, even though the conversion efficiency is quite bad to go from power to hydrogen back to, power to hydrogen back to power. Getting it there is kind of like a firm capacity resource for particularly the last 5 or 10% is really critical. And so we see our grid models usually deploy it because your options at that kind of last stage are really expensive and difficult. So even though it's not a big amount of hydrogen burned, it usually is a very big amount of capacity in terms of your firm capacity for meeting your resource adequacy needs. And so I think thinking about that kind of outsized role that it potentially plays in those certain time periods and also understanding what that means, like how do you operate a system that needs to store hydrogen for much of the year and then for 5 days needs to discharge all the storage almost at once and burn it in fuel cells or hydrogen combustion turbines. That's a very different type of demand than our kind of typical pipeline network, which is feeding gas to turbines kind of like on a more regular basis. So I think there's more challenges there. I don't know that we had to address them all in this paper, but worth kind of starting to think about. For the offshore wind work, it's really a cool study. I don't know if I have too much to add. I think a lot of, I wasn't involved in the Atlantic offshore wind transmission study. I'm familiar with it, so I could speak a little bit about it. Most of the work I do, I feel like, is capacity expansion modeling, which results in a lot of crayon-like maps of transmission drawn across the US. So we're probably a little bit optimistic in terms of what we can do, or at least we're always looking at sort of the potential to what could be done. The one thing I'll maybe just say is that in that study, we was really able to have that offshore backbone that kind of extended all the way up the Atlantic. But I actually think the value of that is probably pretty similar to the value of putting that transmission on land. It's just the fact that it might be easier to build it offshore because you can't site and permit the transmission on land like you described. So it's really just emphasizing the value of transmission, and I think you highlighted this well, but understanding what we can do to move that along is going to be really important.
Thanks. Joshua Hodge. I'm executive director at MIT CEPR, which is basically the Center of Energy Economics at the Institute. I guess, I'd like to sort of challenge the group. Because the Chinese government is subsidizing electrolyzer development, and their system allows for that in a way that our Western systems don't, and it's almost inconceivable in the US, right? Is that really a bad thing? I mean, maybe it is the Chinese who figure out how to get it to $2 a kilogram. And I think that might be a good problem to have. Just a thought, because there are a lot of positives about that system, right? When we're looking at infrastructure, there are also a lot of things out of the Chinese system that we don't really necessarily want in the U.S. and Europe. And I think an argument could be made that we can cherry pick about there. Just a thought, just sort of the glass is half full. Let the Chinese drive down the price of electrolyzers. I think really quick on the next paper. I really like the next paper because you focus on reducing costs. And I also think that, while right now might appear to be a difficult time to move something like this forward, it does strike me that approach potentially solves problems for PJM, like in the relatively near term. And I'm a little more positive. Sorry, I'll just get the names right here. I really enjoyed Professor Almassakhi's presentation earlier. I'm a little more positive or optimistic on the potential for transmission build out than you are. So I'm going to be uncharacteristically positive here, and you guys may never hear me be positive again. Mari's going to, jaw's going to hit the floor. I think there is a case to be made with this coming administration here in the US around transmission. And what I've begun to understand in conversations with conservative civil society, and I'm fortunate to still have a lot of Republican contacts. Mind you, they're pro-climate, Republicans, so one might be skeptical of the influence they would have with an administration such as this. But I have really noticed that when you focus on attributes of expansion of transmission build out, such as improving reliability, system reliance, in many cases lowering system costs, and yes, to be blunt, you don't mention decarbonization explicitly, you'd be surprised who you would get on board. And the thing is, there are many aspects to building that infrastructure out here in the US that are very consistent with many of the Trump administration's, Trump 2.0's administration's stated priorities of building infrastructure, creating American jobs, investing into the country. And I think, an economics argument can be made there that might appeal to them. So the nice thing is if we get that build out, it can be kind of generation portfolio agnostic. I mean, there's nothing preventing us from putting a lot of wind and solar on that down the road if we can't get that now. I'm not sure that'll be necessary because I don't think that they're going to touch the solar and wind tax credits simply because too many Republicans are too long those industries. So what I'm saying, I guess, is if this is correct, and if we can move transmission forward in this administration, it also tees up this conversation about offshore wind transmission. And I think here on the East Coast and with PJ in particular, where you're essentially you could solve a problem that they already have. No, it seems to me a very compelling argument. Anyway, those are my initial thoughts.
I'll let Marie respond first, and then I'll have a few.
Are you sure?
Absolutely.
Okay, because I thought I had so many comments to me that I can hardly remember where to begin or start. But where did you start, Brian?
Maybe one to just think about what price electrolyzers can get.
Yes, right. That is a good point. And I think that maybe we are a bit further in terms of implementing variable electricity prices in Europe, which of course facilitates this flexible demand and the reaction to prices. and prices being also reflecting how much renewables do we have in the system at a given time. So there's that. And then on top of that, we are looking into dynamic tariffs in terms of saying, or tariff deals where we can say, well, if you are willing to be decoupled from the grid under certain circumstances, you can have a lower tariff connecting to the grid. So we're looking, because tariffs is a large part of the price as well. So we're looking both at the possibility to react to prices, but also tariffs that reflect how much you are straining the grid. So I think there's a lot to look into in terms of that. And Joshua, I was just nodding. There was a lot of good comments on your side, and in terms of, I think one of the comments was that, well, I'm expecting that to be driven by a high carbon price. Yes, either we add a high carbon price or we add a cap. And we say, well, we are assuming that you want to adhere to the climate targets. We have zero climate target in 2050 in EU. So drive toward that target, and that, of course, takes a lot of things into account. But there are many question marks, like how efficient and cheap is CCS going to be? But basically what we see, and I think IEA, many others sees, is that CCS is going to be needed for negative emissions. So the fossil fuels have to go out. And that means that this is where we need some backup power, as Brian pointed out. And you are right, this means large capacities standing idle most of the time. Engines, turbines, or whatever are cheap solutions for this. And then it can be okay that the price of the fuel is pretty high for those few hours where we don't have wind or solar, and the transmission capacities can't help us. I do see, we discussed another solution. There are other hydrogen-based energy carriers, such as ammonia, which could also maybe be used, and where you wouldn't have to deploy a huge grid or truck hydrogen around, but could maybe truck liquid fuels around at a bit higher efficiency, lower cost, and still. Thank you. So that's another option.
I just want to keep it moving, because I want to make sure we have time for questions and audience engagement. And for a quick response in the offshore grid study, some of the great benefits from PJM came not from offshore wind, but from building one of these east-west connector lines that we haven't been able to do today. We know how to do it, we just can't. So I think the institutional interests of the various parties involved in the grid are what's stopping this, not the fact that it makes sense from a consumer perspective, a cost perspective, or an economic perspective. And so that piece of transmission is where I think the big challenges are. And so I really wonder what the roles of FERC or RTOs in the future could be, or maybe even a model like a power market authority that's running its own shop offshore institutionally, that would also have powers of eminent domain for beach sightings. I mean, there's different ways to think about this institutionally that could actually potentially solve some of these problems. But onshore transmission, while it makes a lot of sense, of course it does, we all know how hard it is to build, especially in New England. I am excited about the conversation that we're going to have. I would like to ask the presenters to repeat the question when you're answering the question, so the online participants can also hear it. Questions from the audience? And I would like to introduce a new innovation. If you have on the topic we're talking about a direct comment to add, hold both of your fists up, and we have the two-fisted intervention. That'll just keep it a little bit more lively and focus on topics. So any questions for the topics or the panelists, or what you're thinking about this? Is transmission possible offshore Massachusetts? What do you think?
Can I add a while we're waiting. So in the Danish context, we're talking about energy islands. And of course, the point with energy islands being partly that we can build a lot of offshore wind and collect it and bring it to shore. But the other part of the energy islands is to be able to connect to some of our neighboring countries. We have one such situation with Kriegers Flak, where we connect from two different countries to the same wind farm. That makes it possible to take off the wind when it's coming, but it also just makes it possible to have this as a normal transmission connection when it's not. And then on the energy islands, we're also talking about hydrogen production, but that hasn't really materialized yet. So it just at the moment seems like an idea.
Well, and I just wanted to add as a point of clarification, that energy auction that they had was for the offshore wind projects, and it wasn't produce hydrogen, it was to produce electricity to sell. And when Jakob and I were talking last night, and because the idea of the energy islands and how it works, the first one being Bornholm, and you have two willing parties, Denmark and Germany, and you have the idea of having these turbines selling power into Germany. And when I went and talked to my colleague Borisgo at the Danish Energy Agency, he pointed out to me all of the contractual challenges they're having. Two willing partners, great project, everybody wants the power. What if it doesn't get built? What if this doesn't come on? And who handles that risk? Who bears that cost? So it's not only hard here. Maybe that's not a positive take home, but one of the pieces and how those contractual pieces can really stymie some of these really great ideas going forward. Yeah, absolutely.
I get that the auction wasn't specifically for green hydrogen. What I mean there is if you look at the aggregate build that would be represented by this edition, I feel like just in general, the Danish government's push is assuming, well, either demand that is electrification tomorrow or it's coming from somewhere else, or a demand for green hydrogen. And just in my conversations with Danish colleagues over the last few years, folks have been remarkably bullish on green hydrogen demand. So that's, where I'm coming from there. One comment I have, and I'm going to be uncharacteristic again and say something else that's half full. It is very, very true that it is nearly impossible to build transmission in this country. And I think that's probably the greatest single threat to forget deep decarbonization, even meaningful partial decarbonization of the power system in the US. I mean, I don't know why every, environmental NGO isn't out there pounding transmission. Maybe I do, but I would love to see you get a little sophisticated on that front. However, in Texas, this may surprise some folks who don't follow this closely, there has been quite a lot of success in the CREZ project in building new transmission. Now, Texas is unique in terms of the space, where a lot of this is being built. It's certainly not the Northeast, but where I think, Texas has been really sophisticated is in their early outreach to stakeholders. They've had a much more sophisticated system for engaging, folks along the transmission lines than say we did here with New England Clean Energy Connect, where we basically didn't engage anybody until it was stopped.
Well, asking people in New England to say yes to a transmission project has never been a good play.
Right, but the good thing is, though, I think in a lot of the country, following the CREZ template, you can get this transmission built, particularly when you have bipartisan political support, which they did have in Texas for that transmission.
And you had MVP projects in MISO region and others, and yes.
Yeah, I'd be happy to just comment, which is to say, I completely agree. I think we've done a pretty good job here. And perhaps some of our partners, I haven't looked at their some similar program in California. In HDA,
consumers about the energy transition with regard to the changes in their home and their vehicle. And I will try and be as diplomatic as I can be here. Primarily on that step. So I think they have a lot of opportunity for improvement with regard to the estimates and changes that have needed on the transition and distribution systems and the larger pieces that have been decided.
I think transmission is particularly challenging because it's a linear infrastructure. And our current reliance on merchant power lines to build this means that you're having to secure those rights of way up and down. And there's so many veto points in our current approval process. So maybe a more authoritarian approach as outlined in Project 2025 could do something not only for pipelines, which are explicitly mentioned, but also transmission. Well, nukes as well. Nukes come up very favorably, as well as free markets. I don't know how that circle gets squared.
I had a comment to Josh's. I think you are right in terms of were the demands ready in the Danish bids? Were there off-takers ready? And that this includes kind of on the hydrogen side, the fact that we are planning a pipeline from Denmark to Germany, and this pipeline was delayed until 2032. Meanwhile, the turbine, the offshore wind developers had to put up the turbines by 2030, if not receiving a fine. So what do you do in those 2 years? Do you then build a line to cables to take off the electricity and then only use them for 2 years? Or what do you do? So it illustrates the complexity, right? When you have these mega projects, you also need to make sure that you have a matching mega demand to ensure that you get the prices that you need. So it's kind of the challenge is not just on the infrastructure side, but going through the whole value chain, ensuring that everybody's ready when the power comes, somebody's ready to offtake it and utilize it.
Just one thing I wanted to add, given the Project 2025 reference, I don't expect the Heritage Foundation to want to build new transmission necessarily. But what I would point people to is the American Enterprise Institute 2 days ago posted a memo that you should take a look at, which provides an overview of their advice to the transition team. And in that, they push very, very hard on expansion of transmission for resilience and reliability. And they make it very, very clear that they don't want the wind and solar tax credits touched. Now, how much influence American Enterprise Institute, they're more moderate than some of these. How much are they going to have enough influence with this administration? I don't know, but I would definitely encourage people to look at that because it's probably the only hopeful thing that's really come out so far, and at least it is a credible, actor. So look at it. 2 days, December 4th, they put it out. It's on their website.
There's another force called DOE. Also, they're concerned about reliability and resilience for their bases, seeing the growing demand for data centers as a threat, and that they're able to move faster and have more resources, which is a miraculous thing, extraordinary thing to say, and compare anything to DOE. And so I think that's another force there that will, perhaps be helpful.
The Department of Defense has been telling us that climate change is. Sorry. Oh, sorry. I've already failed to do that. I was simply going to say, so he was mentioning that the DoD is concerned about the lack of transmission and looking at data centers and how that's going to impact demand and potentially our energy security. And I was just going to say, what's frustrating though is that the Department of Defense has been concerned about anthropogenic climate change on national security for decades, and for some reason that message has never really gotten through to some of our friends on the Republican side. And I can't really explain that. I'm just reflecting that reality.
On the data centers, I think this was also really debated at the CEPR workshop, and I think that this is actually the second big electricity demand being expected in Denmark, and I'm not even sure that they're taking into account generative AI when they forecasted the demands, because data centers love Denmark because of the cheap electricity, because of the high security of supply. And that is kind of fun because in Denmark, people are saying, well, why don't we do like in the US and build nuclear for data centers? Meanwhile, the data centers are coming to Denmark because of the renewables and the green power, which is cheap and secure.
If I may, sorry, just one thing on data centers for folks to keep in mind. So a lot of sort of red state utility executives are out there marketing their capacity right now because they're not undertaking a lot of voluntary electrification. In many cases, they're not even being pulled to electrification through electrification of transportation. So if you talk to the CEOs of many sort of southern IOUs, they will tell you there is no issue with capacity for data centers. And what you should do is you should move your data centers from California and Virginia and where else into the Southeast. And so I think this is going to become a big story because there is a lot of coal and gas capacity sitting in corners of the country that could be used for this. We'll just have to watch that.
I have Brian in the back. No. Yeah.
Just a comment. It's like we also talked in the last panel about data centers. Look, if we can't handle the amount of data centers that are coming out, there's no chance that we're going to handle the next phase of the new demands that are coming. So I think it's really just a comment that this really needs to be solved. And there is something about that we're talking a lot about in the Danish case, the location of these data centers close to new possibilities for renewables and deployment of renewables. So I think this is an initiative, or like the talk about data centers should be something that also taps into the green transition in general, where we need to understand that large demands or large renewables needs to be placed with existing large demands or new large demands.
And I think that the question was on data centers and demand and the growth and how you co-locate demand going forward. I wanted to follow up briefly on the Virginia, which actually is in the South, but they have such an interesting model with regard to offshore wind. I mean, CVOW is the one offshore wind project that is on time, under budget, and going forward as scheduled. Granted, they secured their contracts before, but the model of Dominion, the regulated utility, getting ratepayer approval and being able to keep the cost down provides not only political legitimacy. They put the two first Ørsted turbines up back in 2014. It's a very popular boating destination for people wanting to fish, and they're having their point of injection on a military base. So they've built this story of that technology in a way that is with the Virginia ratepayers. And I just want to point out that they're also pushing both data center puts, but also small modular reactors. So they're like the one utility, and their point is, we're a utility, we build big. In our restructured markets that are the rest of the maritime East Coast, they don't have that ability to still say, we build big, we build projects and rate base everything. So I think that institutional structure is one that in this country is also shaping what's seen as an endogenous project that we're building, or someone else coming in and driving up the cost for our ratepayers. So any other questions? Comments? I really, one, Mass.
Transmission.
Could you stand up, please?
How about the transmission question? I feel like the next administration would be really happy to take accolades for big projects. I feel like transmission, there's no way you can do that in 4 years or 8 years. And so you're just taking a risk as a politician today to build a project that's highly risky. So I'm curious, how do you guys think policymakers, even if they get together, how can they share a win out of transmission if it takes 10 years to build?
So my project on this that I've studied onshore transmission for decades, right? And my favorite one is Minnesota's CapEx 2020. And they hadn't built a transmission line in Minnesota for 30 years. And I knew some of the regulators there. And their first memories of transmission in Minnesota were back in the, do you remember Paul Wellstone? That's where he got his start, was opposing transmission in Minnesota in the 70s. And there was a group called the Volt Eagles that was opposing a cross-state transmission line that the utility sided without consulting anybody. And you had 14 transmission towers tipped over by farmers on tractor, live transmission towers, right? And so Paul Wellstone got a start opposing these lines, and this guy, Claire, was saying, not on my watch. And so during CapEx 2020, they realized very early on that they weren't going to be able to meet the Minnesota renewable standards unless they built transmission. And they were, all of the communities across 6 states. That became the basis for MassCEC's $6.2 billion MVP project, which upheld the challenge, which was sustained a challenge in the Ninth Circuit. And so you really have a very different story of how it's happening. And it happens by a lot of hard work on the ground with people. But the craziest story from how they allocated costs on this, because everyone knows the joke, the only person that likes transmission is a transmission engineer. Right? But how they allocated costs across these projects and all the utilities was using not a fancy model or an economics, but poker chips. Everybody was given poker chips based on their load. They put on the projects they could actually fund. They did a backroom deal, and that's how they did it. So the politics and the institutional cooperation for this, it's hard and it's possible with the right people.
Yeah, so I think this administration is actually really well positioned to build the transmission if they want to. And I think the motivations are even fairly straightforward. So while it's true that we have to wait for the completion of the line to benefit from the economic improvements related to lower systems costs and resilience and all this, these infrastructure projects are expensive and employ a lot of people. And you can run up the score in a hurry. Particularly with transmission, where you can choose where you do it, right? So you can be very strategic, and to the extent that the Trump administration is not only interested in his legacy, which apparently, what I'm told, that once the retribution phase is over, it's all going to be about his legacy. Take that for what it is. That sort of want to be reelected, if you will, that they'll have a vested interest in investing heavily in jurisdictions that matter into the Electoral College. So I know this is a bit of a cynical take, but I think that, hopeful. Well, I mean, it's both. It's both, right? I mean, it's the classic making lemonade out of lemons. I think I am weirdly optimistic about the transmission piece. I am. I have to admit, yeah.
With that note of optimism, I would like to thank everybody for engaging with us today on these important topics in the future and for coming and being part of this. Thank you, everybody. And thank you to Torben for your excellent hosting and taking care of us all. Thank you.
I will not pretend to sum up what has been said today because I have not the ability to do that. But I think that we all have had some thoughts and ideas to digest. And speaking about digestion, there will be lunch. It is served just outside, so please go ahead and grab a sandwich in a few minutes. But just to repeat myself, that the connections that we have built for the past 2 years and the knowledge that we have shared really lay a strong foundation for what we have to discuss in an hour among CANSI, which is CANSI and beyond. What do we see as future collaboration? And I would like to emphasize this is not a closed club. Everybody that would like to chip in with ideas and participate, they are more than welcome. So I just want to say thank you so much to all the presenters, to the panelists for the participating in person and those online. Thank you so much for being here. All the good comments and ideas are recorded, so you can revisit that. We will send out a link if there's a few of the good ideas that you have forgotten. You can revisit that on the YouTube channel of Innovations in Denmark. Thank you so much.